Don't swear. Okay, people will be allowed to come in now, and it's already 2. Hi, everybody. We are just getting ourselves sorted out here. Oh.
Sarah, can you hear me?
Someone has a lot of background noise.
Okay, to all of our participants, could you please mute yourselves and let us speak in? We have a lot of background noise and that will help. Raul, could you please mute yourself? Raoul, could you please mute yourself? There we go. Okay, I just muted Raoul's microphone. And that. Oh, all right, now we got a lot more too. And people who are just coming in, I'm turning on your microphone capability.
Elizabeth, I'm going to share my screen.
Okay. Yeah, great. Thank you. Sarah, it's great if you can take over that part of it, because now we'll have to get Colin back in.
Right. Here we go.
Colin's back.
Colin's here.
But I'm going to ask him to unmute because we can't hear him.
Can you hear me now?
Yes, thank you, Colin. Colin, just so you know, Sarah is technically the hosting now because something started acting oddly with my system, but you and I are actually, Sarah, will you please make Colin a co-host?
Yeah.
Thank you.
Oh, the problem is I can't do the slideshow and that at the same time.
Then stop the slideshow and make Colin a co-host. That's
right.
For a
You're
moment.
not able to do that.
Just for a moment.
Here we are.
Great.
Colin, you're a co-host.
Great, thank you. Now you can run this, put the slideshow back on.
Slideshow back on. Maybe I can now. There.
Great, thank you. While we're getting started, everybody, we're running a slideshow that shows the schedule and some housekeeping details about where your mute button is and a couple of other things. So this is just a short 4-slide show that we're going to run for a few minutes while everybody's checking in and until Colin's ready to start. For those of you who are just arriving, I'm continuing to give you permission to talk. So you can say hi to each other if you want to, and you can ask questions during the course of the day. When you're not talking, it would be great if you could please mute your microphone, mute yourself. That will help to cut down on background noise. Thank you. Great. Okay. Sarah, do you want to stop the slideshow,
yep.
and Colin can get underway, please? Thank you.
We're all set?
We're all set.
Okay. Thank you, Elizabeth and Sarah, for all the work that you've done with this. I would have been lost if I had to do this myself. Well, I'd like to welcome all of the attendees. I know it's not exactly the forum that we probably would have had in mind at this time a year ago. It's still something I'm kind of getting used to, all this video conferencing. So I'm about to begin a PowerPoint that I've prepared as an introduction. But before we dive into that, I want to underscore that I'd like you to feel free to jump in at any point if you have questions or comments, because I find that these types of meetings are a lot more enjoyable when there's participation from the audience as opposed to just an endless lecture. And in fact, I'd like you to kind of think of it as an informal conversation between us rather than a formal lecture type setting. Now I'm going to share my screen and I will begin the PowerPoint that I mentioned. So bear with me for just one moment, please. Can everybody see the PowerPoint that I have on screen? I don't hear any objections, so I will assume that everybody can view it. So my name is Colin Littlefield. I'm an observational astronomer at the University of Notre Dame. And for the past few years, most of my research has focused on observations from the Tess spacecraft and also its predecessor, Kepler. And one of the things that's really impressed me about it is that there's just so much data that's produced by these two missions, particularly Tess, that professional astronomers literally cannot keep up with it all. There are just so many different research possibilities that have been completely untapped. And it's really fertile ground, I think, for amateur astronomers who are looking to do something more than just using their own equipment. For example, if you live in a city and you can't see the stars at night, this is a really interesting way, I think, of getting involved with research. So first, let me give you kind of a roadmap for what I have in mind today. And excuse me if I seem distracted. I've got Slack set up here on my phone, and it keeps pinging with alerts. And I've got to keep an eye on that just to make sure that that there's nothing wrong technically with the workshop. So the roadmap for the workshop, there are going to be two sessions, both of them 2 hours. And the first one is going to focus largely on Tess from an introductory perspective. So we'll talk about what it is, what the science applications are, and that kind of thing. I'm also going to show you a few web-based resources that do not require any computer programming expertise at all to use. You literally just visit these websites in your web browser, and you can use them to determine, for example, whether the Tess spacecraft has observed a particular target, and if so, when did it observe it? And then we're going to shift gears a little bit and probably spend about the last hour of the first session discussing Lightkurve. And my hope is that everybody will be able to follow along using the notebook that I sent about 15 minutes ago. You don't have to worry about opening it now. We'll get to that in due course. But we'll start to work with some sample test data sets that I've looked at that I think would be really excellent as introductory targets. And we'll discuss how you download them, how you analyze them, how you identify systematic issues with the data, that kind of thing. And the second half of today is going to be dedicated to data analysis. So being able to determine which periods are present in a Lightkurve, that kind of thing. And we'll be using VSTAR, which I chose because it's supported and actively developed by the AAVSO. And it just made sense because a lot of amateur astronomers already use it for their own research. And it turns out it's actually pretty powerful stuff. And it works very well, I think, with test data. But that's the second half of the session, so I don't want to focus too much on it right now. And then the very last part of the meeting, I'm hoping to split everybody up into two groups, depending upon what interests them, eclipsing binaries and short period pulsators. And I have a list of targets that you can look at. And a few of them, actually all of them, I think, but a few in particular, I think they have surprises in the Lightkurves. And if you compare those Lightkurves against the current information in the AAVSO VSX, you'll actually find that you can improve the VSX data for those stars. So lots to do today. I think it's really cool stuff, and I hope you do as well. I think it's also useful, given the novelty of this workshop and kind of how ambitious it is. I want to outline what I think will be a successful outcome, because I know that some of you already have Python experience. Others have never used it before. So there's a very wide range of experience level and comfort level too, just with computer programming. So I don't want you to feel like if you're a beginner with Python that you're already behind the curve. because I'm expecting that most people will have very little experience, and I've planned accordingly. But at the very least, I think that very reasonable objectives for everybody, as I've listed here. By the end of the day, I hope you can be able to describe the general science purposes of Tess and how they relate to variable star observing. I'm also hoping that you'll be able to tie it in more specifically with your own personal research interests. So there are some types of variable stars that I don't think are very useful if Tess looks at them, whereas there are other variable stars where Tess can just reveal an unbelievable amount of information about them. And so hopefully by the end of today, you'll be able to identify which classes of variable stars would benefit from Tess. And then there will also be an ample discussion of the nuts and bolts of Tess observing. So I don't expect everybody to know all the details because I don't think it's necessarily difficult. But if you're encountering it for the first time, it's going to seem much worse than it actually is. So as long as you have a kind of a general familiarity by the end of the day with how to analyze test data, I think that that would be a major victory from kind of the more technical side of things. And then also after the workshop, the AAVSO leadership and I are very interested in making sure that this workshop develops momentum towards a higher goal, which is to advance the science mission of the AAVSO and also to benefit just AAVSO observers who want to use this new and powerful source of data in their own research. So I've listed on the screen here four possible avenues of exploration after the workshop. It's not exhaustive. I'm sure there are other possibilities too, but I want you throughout the workshop today to be thinking about what we can do, what you personally can do after the workshop. And on my part, I'm going to commit to helping each of you individually if you want to continue with Tess analysis after the workshop is over. So I'm not just going to do this workshop and cut you loose after that. I'm committing to working with you long term if you're interested. And finally, just a reiteration, please jump in at any point if you have questions or comments. So let's begin with just a general overview of what TESS is. So TESS is an acronym, Transiting Exoplanet Survey Satellite, and it was primarily designed to detect exoplanets. So it would look at a large number of stars. It has an enormous field of view, as you can see there, 24 degrees by 96 degrees. And it would monitor the brightness of all the stars visible to it for 4 weeks continuously. And it would look for tiny dips in the light curve when a planet passed in front of the star. Many of you are already familiar with this technique, the transit technique. And in fact, a lot of you, I'm sure, have actually done this with your own equipment. The idea with TESS is that it could identify new exoplanets just by virtue of the fact that it was looking at so many targets simultaneously. And in a moment, I'm going to show you a video clip that illustrates how it's been surveying the sky. We often say that TESS has all sky coverage because over the course of time, it does look at most of the night sky. But the truth is it has to divvy it up into tiny slices that it observes for 4 weeks at a time, and then it reorients itself. So let me switch now to a brief video clip that will illustrate this.
Each of Tess's cameras has a 16.8 megapixel sensor covering a 24-degree square, large enough to contain an entire constellation. Tess has 4 of these cameras arranged to view a vertical strip of the sky called an observation sector.
The coverage of the Tess cameras is unprecedented in terms of the amount of sky that they can actually see at any given time, and also their ability to cover such a broad portion of the sky. The types of targets that Tess will allow us to find will enclose essentially all of the bright nearby stars.
Tess will watch each observation sector for about 27 days before rotating to the next one, covering first the south and then the north, to eventually build a map of 85% of the sky. This coverage, about 350 times what Kepler first observed, will make Tess the first exoplanet mission to survey almost the entire sky. Tess will fly in a highly elliptical orbit that maximizes the amount of sky the spacecraft can image, and is carefully timed with the orbit of the moon. It will spend most of each 13.7-day orbit collecting data, and then, as it passes closer to Earth, it will transmit that data to the ground. Because Tess's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope.
So there's more to that video than that, but I wanted to limit it, just to the most relevant portions. And the takeaway from that I hope you got, was just the manner in which it surveys the sky. So I'm about to jump to the next slide where I discuss some of the jargon that you might have seen there. But before I do, just a couple more points here. First of all, the idea is that you're going to have about a 4-week-long light curve for 85% of the night sky. It's just that it won't be simultaneous. One of those sectors will have a 4-week light curve, then the next one, and then the next one. And it would be, I think, constructive if you think about some of the observational biases that this can help to break compared to, say, ground-based observing. So we'll get to that a little bit later, but it's just something useful, I think, to keep on the back of your mind. So jargon, unfortunately with astronomy, you just can't get around it. And there's some jargon that with Tess that you'll encounter quite often. One of these terms is cycle. So each year of the Tess mission is referred to as a cycle. And cycles 1 and 2 have already been completed. 3 is underway right now. Cycle 1 surveyed the southern ecliptic sky, and cycle 2 surveyed the northern ecliptic sky. You also heard in that video that Tess observes in what are known as sectors. So a 4-week-long pointing where the spacecraft holds its orientation very precisely, and then it reorients itself to cover another sector. And there is a small amount of overlap between the sectors. So there are some targets that will actually have almost a year of observation. Others, maybe it won't be a full year, but they could have been covered for multiple sectors. So potentially months, which is, of course, a good thing. And then a couple other points about the types of observations that Tess obtains. You'll frequently hear references to so-called FFI observations. It's short for full frame image. And the idea is that when Tess is taking data, that it will have a full frame exposure from all the sources that are visible to it with a 30-minute integration time, and it will continue doing that throughout the sector. There are a small number of pre-approved targets where the interval between images will be 2 minutes. So those might be, for example, cataclysmic variable stars, where there's extremely rapid variation on timescales of minutes and even less than that. So it's competitive to get the 2-minute cadence. There aren't a whole lot of targets with it. And I think generally, if you're trying to ask yourself whether Tess observations might be useful, you should probably assume that a target, if it was observed, it would be a 30-minute cadence, which is the default. Now, it gets a little bit more complicated than this because things changed a little bit in cycle 3, which I mentioned is underway. So during cycle 3, the full frame exposure time is been reduced from 30 minutes to 10 minutes, which is good because it means you're going to get more time resolution in the light curves. There's also a new 20-second observing cadence, which is extremely competitive, and there are only a handful of targets, I think, that would be really compelling for that. So for example, there are some stars where astroseismology would really benefit from that very rapid exposure time. But I think the takeaway here would be that you should assume that a particular target would be observed at the full frame cadence. So 30 minutes in the first 2 cycles, 10 minutes in cycle 3. You shouldn't expect that there will be the really fast photometry for your target. And now that we've done kind of some of the esoteric jargon of Tess, I think it's kind of worthwhile just to step back and look at a couple of the major science accomplishments of the mission. So this one is very recent, and you may have seen it in the news when Tess discovered an exoplanet that was eclipsing the white dwarf that hosts it. And this was a major breakthrough for a number of reasons. One of the major ones is just the fact that planetary systems can survive the evolution of a main sequence star off the main sequence until it forms a white dwarf. The fact that you can still have a planet after that, and that was reasonably close to the white dwarf itself. There were just many, many interesting implications from this. And it's kind of a classic example of a discovery that only Tess could do, because there are many white dwarfs that are known in the sky, but monitoring them continuously for transits is a Herculean task, because there are just so many of them, and it's just not practical to expect ground-based equipment, for example, to be able to monitor them closely enough to be able to detect an event like this. And another one, involving a tidal disruption event. So this is where a star approaches a supermassive black hole and is tidally disrupted by it. So these are unpredictable events. They occur at cosmological distances from the Earth. So there's no way you can know in advance that there's going to be a TDE. And the only practical way of detecting them is if you cast a really wide net. So you look at a large area of sky, you catch a lot of galaxies in there, and you hope that just by chance there's a TDE in one of them. It's very much like trying to detect a supernova. You just need that luck that one goes off right in time for a survey to detect it. And in this case, Tess provided exquisite coverage of the TDE. So it caught it before it started to rise and also during the rise in the light curve. And it provided just unprecedented insight into the phenomenon. So I've spoken highly about what Tess can do when everything goes right. But that might leave you with kind of a misleading picture about it, in the sense that it sounds like it magically returns these wonderful results. But the reality is that the spacecraft has limitations, and so we should discuss what they are, because some of them, I think, will probably take you by surprise. So the first one that's, I think, especially jarring is the angular resolution of Tess, and even worse, the point spread function, so how large the stars appear on the detector. If you'll focus your attention on this figure here, so the upper right-hand part of the slide, I have 2 images from a paper that I put out last year. The left one shows a digitized sky survey image of a field of a variable star that I was writing about. I've indicated its position here with this circle, and the square indicates the field of view of Tess. So this is what it looks like with reasonable angular resolution. The right-hand panel there shows the same field as seen by Tess. And the first time I saw this, I couldn't make head or tail of it because the image is just so blurry compared to what you see at the left. If you look at it long enough, you can start to match up some of the stars. So these three here, for example, correspond with that streak right there. But it's really striking, I think, when you see that the stars aren't really seen all that distinctly. They're very heavily blended with each other. And then even worse for me, at least initially, these two pixels that I've highlighted here, the blue rectangle, those are the pixels where my target landed. And when I first saw that, my reaction was, oh no, I was looking forward to this for months and it's nothing but a blur. And luckily, it turns out you can still get really good data from Tess, even if it's blurry like this. But it's still, I think, something that takes some getting used to, that an image like that on the right can still yield, excellent science.
Excuse me, Colin, before you go on, I had a question that I was unable to ask because of the muting issues. You mentioned the different cadences that Tess has.
Yes.
Are there ways for us to actually determine before we look at a given source what the cadence is? Or is that something where you will have to do your exploration yourself to determine the cadence?
So that's something that we'll cover when we switch over to Lightkurve in the second half of the morning session. The short answer is yes, it's fairly straightforward, I think, to determine which cadence was used. So when you run the notebook that I provided, it will actually list whether or not it was full frame or the 2-minute cadence for cycles 1 and 2. I think a little kind of on a more abstract level, if you're just trying to plan ahead, you're trying to think in very broad terms about what Tess can do for you, you should assume that it probably only observed your target at the full frame cadence. It's unlikely for any given target that there will be 2-minute cadence for it, as a very general rule.
And just as a quick follow-up, and maybe I apologize if you are going to cover this later, but since part of data mining is this exploration of parameter space, are there ways in which you can actually, rather than saying I want to look at source X, is there a way of listing all the different sources that are covered by, for instance, the fast cadence, and then starting to go through those?
Yes, and actually, when we were planning the workshop, that was a debate that we had back around February, because that's an entirely different way you can go about this. So if you're looking more at the data mining, kind of that really wide net that you mentioned, where you just look at all the targets. I know of several groups that are doing that actively. And in fact, one of them actually uses amateur volunteers for their work, and they've had some really fine results. In terms of the strategy of the workshop, we decided not to go with that approach for a couple of reasons. First of all, it was Windows only for the software, and my recollection is that the software, there might have been a licensing restriction with it, or it was not free and open source as Lightkurve is. So that was kind of a big issue, that we wanted to reach as many people as possible. The other concern that I had was just that those other groups have such excellent resources available to them that we were concerned that amateurs might not really be able to compete with them. Compete is probably not the best word there, but when you have groups that are data mining Tess with the resources that are available to them, it would be difficult, I think, for individual amateurs to really make their own mark against that kind of competition. Whereas with this approach, even though it's a little bit more targeted, we decided that it was probably something that would give amateurs more room to find their own way and not have to constantly be competing against those impossible odds.
Thank you so much. That's a great explanation of the sort of the two different ways one can do the research and some of the pros and cons for the different method. That's really helpful.
Well, thank you. So unless anyone has other questions about that, it's a worthwhile discussion, and I think there's more that could be said if anybody wants to jump in. If not, I'll just continue with this slide.
Yeah, I've got a very, very sort of simple question. What's the magnitude limit of Tess? How faint can it go? And does it saturate at all?
Two excellent questions. So first with saturation, there's a procedure that you can do called halo photometry. And actually I picked out a star later on, Alpha Draconis, otherwise known as Thuban, that we'll look at. It's a very bright naked eye star, and it was discovered to be an eclipsing binary by someone who was analyzing test data. And the fact that you can detect those eclipses and characterize them really well with a naked eye star, it should tell you that there's you can go very bright with Tess. You just have to know how to deal with the data, but it's not difficult. The faint side of Tess, I think, is a trickier question to answer because it's really driven by your science. So I like to observe cataclysmic variables, and there you don't need as high precision for some types of CVs. So if the variation is like 1 magnitude, peak to peak, you can have pretty high error bars there on individual measurements, and you can still get great science out of it. Whereas if you're trying to do exoplanet transits, you need much more signal to noise ratio. So you won't be picking out very faint transiting exoplanets with Tess. So if that seems like kind of a vague answer, it's because I think that there are many different possibilities depending upon what your science is. And the truth is, even with the work that I do, I'm still discovering what the faint limit is with Tess. It's just so dependent upon many different considerations, I think.
Okay.
And in fact, here, the next point in this slide actually illustrates, I think, one of the reasons why this is kind of difficult to, why it's difficult to give a firm answer on that point. So I'll draw your attention over here to this figure, and it's illustrating the wavelengths at which Tess is sensitive. And it also, for reference, draws 4 different band passes that amateur astronomers very commonly use. And it doesn't really match up with any of them. So it's redder than the cousin's R band, but it also is much wider than cousin's I, and same is true for the Z band. So it's very difficult to compare Tess observations with observations that are obtained in a standard bandpass. And this also means that, for example, if you're interested in observing a star with a known V magnitude with Tess, the signal to noise ratio that you'll obtain with Tess, so essentially how the size of your error bars with each data point in your Lightkurve, it's really going to be driven not so much by how bright it is in V, but what's going on out in the near infrared part of the spectrum, which isn't always all that well known. So it's a little bit of getting used to. Now there is a tool for people who want to propose Tess observations where they can enter in the spectral parameters of their target, and they can get an estimated signal to noise ratio with Tess. But at least in my experience with cataclysmic variable stars, the spectral parameters are so variable if they've even been they've even been constrained at all for a given target, that's usually not all that helpful. So I usually just propose for targets that have a decent science case, and I see what Tess can do with them. Some of them have been disappointing. Others have just completely exceeded my wildest hopes. So I think it's just something that you learn from practice. A couple other considerations with Tess. The aperture is really, really small. It's about 4 inches, which is one of the reasons why it doesn't go all that deep. Conversely, its predecessor, Kepler, had a much larger aperture, about a meter. And so it actually did really well with fainter objects. With Tess, though, that's not the case. And I think there's also a misconception that just because it's in space, that people assume that the data quality is pristine. And the truth is that even with Tess, there's still systematic issues that you have to be able to identify and correct for. The big one is scattered light, which you'll have plenty of experience with by the end of today. It's not as though it ruins the data, but it's probably the most common issue I see. And it's just something you learn to recognize. I'll show you a couple of ways that you can spot issues resulting from it. So in terms of stating kind of the science case for Tess data, when it would be most useful for a particular type of investigation, I've provided a couple of examples here. So the top panel, if we have any CV people here today, the top panel shows a light curve of a super outburst of a dwarf nova. And the reason I chose this particular example, first of all, it really made my day a couple of years ago when this light curve came out, because it was one of the targets I had requested. And I was very, very happy to see how exquisite it was. But the reason I've chosen it for this particular slide is that it captures the very beginning of this super outburst. So this particular target, called Z-Cha, is normally in a quiescent state, like down here, if you can see my cursor, where it's rather faint. And then every now and then it will experience a super outburst when the accretion disk around the white dwarf becomes hot and viscous, and it accretes onto the white dwarf. Most of it does. The trouble is we don't know in advance when this is going to happen. It occurs a few times a year, but unless an amateur astronomer just happens to be looking at it at just the right time, you'll never catch that initial rise into the super outburst. And here, we caught the entire thing. And this particular light curve is just amazing because you can see these regular eclipses every couple hours. So those are the sharp dips. And then during the super outburst, there are several additional periods that appear in the light curve. CV people will know those as super humps. The jargon specific to CVs, though, is not important for our purposes. I just want you to see this light curve and to realize the benefits of just having Tess looking at the right place at the right time, and how it can capture something that would otherwise be very difficult to observe by other means. So in this case, the first day or two of that super outburst. So the primary goal, I think, when you're using Tess data should be timing analysis. And this means being able to look at a light curve and determine what the period is. And in many cases, perhaps the more salient question is going to be how many periods are there, and what are they, and how do they change with time? So there's some really sophisticated possibilities that you can explore with different types of variable stars. And for example, with my friend Z-Cha here, one of them is that the period is constantly changing for about 10 days of this light curve. And with test data, it's surprisingly easy to be able to measure the change of the period throughout that super outburst. In ground-based data, you can start to do this, but it's subject to many ambiguities, particularly if you're just one observer observing from one location, where maybe you'll get a light curve for a few hours every couple nights if the weather's good. You just can't do that level of period analysis. And with tests, it suddenly becomes, I don't want to say trivial, but it's very feasible to do. And I've already mentioned that Tess is excellent for unpredictable phenomena that just occur randomly over the sky. So for example, TDEs. But here again, it's useful, I think, to identify cases when Tess isn't particularly helpful. I should qualify this by saying that probably I'm sure there's someone out there who could probably raise objections to some of these points, but you'd probably need a very sophisticated analysis, I think, to get around these. And so I would say that Tess is probably disfavored for each of these areas that I've identified. So as an example, astrometry, the 21 arcsecond pixels combined with the even worse point spread function, it means that the signal from a particular source is going to be spread across multiple pixels, so almost an arc minute potentially. And you can still get some astrometry from that, but it's just not going to compete with ground-based astrometric measurements. Another one I think that will catch a lot of people off guard is that Tess is not suitable as a general matter for placing stellar magnitudes on a standard scale. So you can imagine types of variable stars where ground-based observers need to transform their data. So perhaps with a long period variable where they observe in B and V, and they transform their data to maximize its accuracy. With Tess, you just can't do that for a couple of reasons. First of all, there's the weird bandpass that just does not directly match up with any other one. There's also the issue of blending, that whenever you look at a source in Tess, you've got to acknowledge that there's an excellent likelihood that it's going to be blended. And for fainter sources, the blending can be extreme. Another area where I would say Tess isn't especially useful would be for very long period variables. So one of the AAVSO's top targets, Myra, plotted its light curve at the right-hand side of the screen. And that's just the most recent 1,000 days of observations. You can imagine that if you get a 4-week light curve at just some point in there, it's really not going to add that much science value to it, just because you'll see a little bit of a trend, maybe. But Myra is varying on time scales of about a year, and Tess just isn't going to offer much insight into those variations unless maybe you get a Myra star that happens to land in the continuous viewing zone where there's a year-long light curve. But even then, that's not really going to answer kind of the interesting long-term question about what the period is. So if you normally observe long period variables, I would say that Tess probably isn't going to be as relevant to you. But again, I want to qualify it by saying that you could probably think of some unusual science case where maybe for that type of star, you could still use Tess. It's really driven, I think, by your creativity and your knowledge of the science. And we've already mentioned that Tess does not do as well on faint sources, and it does not observe targets near the ecliptic, which is kind of annoying to me because I had a number of targets I was hoping it could get to over the course of its mission, and unfortunately, they're all too close to the ecliptic. So I'm hoping in a future year, Tess might look a little bit closer to the ecliptic and catch some of them. Just give me one moment. So at this point, I'm going to start to transition a little bit towards more of the nuts and bolts of how you do science with Tess. So I think this would be a good spot to ask for any lingering questions that people might have kind of about this general overview I've given about Tess. And if not, I will begin with this slide.
What is the anticipated duration of the mission of Tess?
So originally it was for 2 years, but then it was extended. I'm not sure how much it's been extended now. I'm pretty sure it's at least through cycle 4. I don't know if they have cycle 5 yet. My suspicion is that it's just going to, they'll probably keep renewing it as long as the spacecraft remains functional. But don't quote me on that, and I don't want my words used against me if by some horrible stroke of bad luck that it gets canceled prematurely. But the science yield from Tess is just so fantastic, and the science yield from its predecessor was also spectacular. And it's hard to imagine that it would be canceled if the spacecraft remains operational.
For those of you who are not used with NASA, they are almost always allocated a very short initial mission, and then they can last for many years afterwards, as Colin said. So things like the Hubble Space Telescope, Chandra X-ray Observatory, etc., have been going for nearly 2 decades or more, and their initial missions were a fraction of that.
The other impressive thing when you think about it with the predecessor to Tess, Kepler, even after its original mission, it continued. So some of you may know it had several major failures on board relating to its gyroscopes, which are what enable it to point and maintain its pointing. It had 4 on board, needed 3 to point and hold its position, and 2 of them failed. And the NASA engineers were able to come up with an ingenious solution to this problem to extend the lifetime of the mission, basically by using solar radiation pressure to balance the spacecraft so that even though it couldn't maintain perfect pointing stability, it was able to maintain reasonably useful pointing stability so that it could still observe large patches of sky for about 80 days at a time. And there were some data quality issues because it would wiggle back and forth because of these pointing oscillations. But the fact that they were able to salvage something out of the spacecraft even after it had major systems failures, I think was just mind-boggling. And that too, we'll get to this later on, but the Kepler archives are another avenue of exploration, I think, that you could potentially pursue after this workshop. But we'll get to that in due course. Were there any other questions or comments before I jump into this slide? Okay, then, let me begin by showing you each of these 3 tools. So I have them pulled up in my web browser, and I'll jump over to them. But just a quick overview of what they do and when you might want to use them. So the web viewing tool is extremely easy to use. You just need coordinates or the name of a target. You plug it in, and it will tell you exactly when it was or will be observed by Tess. And it's updated regularly, including future observations, especially whenever they, I'm losing my voice a little bit, especially whenever they update the pointing of future observations. So it's an excellent resource to have at your fingertips. The NASA MAST archive is one option if you're looking to download Tess observations, but you don't want to do so using a Python interface. So I think the usefulness of this particular option is fairly limited in the sense that you can download the 2-minute light curves this way. But if you try to do the full frame data, actually using either of the last two options, NASA MAST or TestCut, you run into an issue that the full frame data requires additional work before you can get a light curve out of it. So there's what's known as a pipeline that will automatically produce light curves for the 2-minute data. But as of now, there is not for the FFI data. I'm kind of hoping that they'll do that at some point so that you'll just have access to these pre-computed FFI light curves. This is going to be more of a technical point that we'll discuss later on when we jump over to Lightkurve. But without further ado, let me just show you what these three sites look like. And I should add that when I'm done with the workshop today, I will send you these slides, and I've put in hyperlinks on this slide to each of the resources. So don't worry about trying to jot down the URLs. Wrong tab. So here's the visibility tool. You just type in a particular target. So I'll do a couple here just for demonstration. And you'll probably see my bias towards cataclysmic variable stars here. So one of my CVs that was observed continuously during cycle 2 is called EP Draconis. Just type it in, hit submit, and then a couple seconds later, it'll give you a full list of when it was observed. So you can see it was not observed at all in cycle, oops, sorry about that. You can see it was not observed at all in cycle 1. Then cycle 2, it was observed all 13 sectors, and it gives you the exact dates here. And then cycle 3, which went to the other half of the sky, wasn't visible at all anymore. But it was really exciting whenever one of these new sectors would come out, just gradually building up that year-long light curve of this really cool star. And then just another fun star that hasn't been observed yet, unfortunately. FO Aquarii, and I see it's still not scheduled to be observed at any point, so hopefully at some point that will change. If you have a long list of targets, you can upload them as a CSV format. So for those of you who aren't familiar with the jargon there, CSV, comma separated values. So you can just do that in a text editor, and they give you the information you need there on the format. It's very easy. Just write ascension, comma declination in decimal format, and that's useful. For example, if you want to propose for a particular target, or maybe if you're interested more in identifying which targets were observed from a huge list of an entire class of variable stars. It's like if you had a list of all the RR Lyrae stars, you could see which ones had been observed that way. And I'll point out one last feature here. If you want to try to get the estimated signal to noise ratio of Tess for a particular source, and you have magnitudes for it in any of these band passes down here, you can use this tool to get an estimated SNR. But I mentioned earlier that it isn't always going to be useful. And if you're looking at highly variable sources like cataclysmic variables, in my case, it doesn't always give the best results. But on the other hand, if you're looking at a source that's reasonably stable. So maybe a delta Scuti star that stays approximately the same brightness. This would probably be a lot more useful for that type of science work. So I'll jump over now to the MAST archive, which I've already, I took the liberty of loading it in advance because sometimes it can be a little bit slow. And I plugged in up here the name of a source that I was interested in, the 808 Origi. And you can, if you were so inclined, you can limit it to just Tess observations that are returned here. But this returns a whole list of different observations of that particular part of the sky. And you can see at first glance, it looks like there are actually a ton of observations here until you scroll over a little bit. And you search, if you look over for, let's see, I don't think I went far enough. Here, the very final column where it says distance, you can see most of these data products that are listed in this table here are actually a fairly large distance from the target that I specified. So for example, there's a Tess Lightkurve here, except the target was 5 arc seconds away from the 808 Origi. And there are only a handful of observations here that show a distance of 0 from V808 Origi. In other words, the ones that show a distance of 0 are the only ones that are directly of the target that I wanted. And if I scroll back over here, you'll see that that top one of the 2 Tess observations, that was the only one with a distance of 0 from the target I specified. And it's an FFI data set, unfortunately. I'll point out this one though. If let's say that I had specified this other target that appears directly beneath it. So again, this is just some other random target that happened to be near V808. But it's not actually the data set that I want. This particular interface will let you preview what the Lightkurve looks like. So I just click on this button here. It'll take it a moment, and then it'll give me a preview of what that 2-minute cadence Lightkurve looks like. And in this case, I think it actually looks pretty interesting. Certainly, it's a high-quality Lightkurve. So again, that's just an option if you want to download data without having to go through Python. You can get pre-calculated 2-minute cadence Lightkurves that way. Full frame data, though, you could download it, but it won't give you a pre-computed Lightkurve like that.
Colin, should we always be using things with 0 offset, or are smaller offsets that are non-zero also okay?
I would never trust exactly 0, or a little bit more accurately, I'd probably allow for some positional error. So you, depending on which source for coordinates is queried, they might disagree by a few arc seconds, especially if you're looking at something with a high proper motion. And so it makes sense if you're specifying a search radius, probably make it non-zero, but you don't want to make it too large. The benefit here to a search radius, like say 5 arc seconds, is that then you wouldn't see all these other data products just pop up spuriously. Because when I checked this a couple hours ago, my initial reaction was, wow, there's a 2-minute Lightkurve for this target. And I thought there wasn't one. And then when I scrolled all the way over to the right and I saw it was a totally different source, it kind of dashed my hopes. So I guess the takeaway would just be make sure you pay attention when you use this particular resource. Pay attention to which target is actually showing up in the table. And it's a good idea to specify a search radius just to avoid getting spurious data products. Were there any other questions? Oh, go ahead.
Obviously, the field of view for the camera is very large, and now we're getting a light curve on a point. Exactly what takes place between that massive field of view and this final product? Or is that too detailed to get into right now?
No, I think that's a tractable question, I think, to answer now. So the way that Tess works is that we talk about 30-minute integrations and 2-minute integrations, but actually what's really happening on the spacecraft is that it's taking much shorter exposures, I believe 2 seconds, and it adds them together, actually very similar to a technique that amateur astronomers would use, where they take short exposures and then they add them together to achieve a longer exposure. And so Tess is doing that continuously throughout the sector. And then at designated intervals, it will read out the detector and store that frame into memory on board the spacecraft. So it adds up all those 2-second integrations into a longer exposure, saves it, and then takes the next integration. And then you might recall from the video earlier that whenever the spacecraft approaches Earth, it will downlink data. And so that's when it'll have a chance to transfer data to the ground, so that it doesn't have to just keep storing all this on board the spacecraft. Once it's been downloaded, there's data processing that takes place. So I think I mentioned earlier that there's a pipeline, and for the fast cadence observations, so 2 minutes or more recently the 20-second mode, what will happen is that those observations will receive processing that makes them suitable for scientific analysis. So the big thing that happens is that the background is subtracted. When we work with test data in a little while, you'll see that the background can be extremely bright and also it can vary a lot across the observation. And that's a pain in the butt to have to correct it with the FFI data. The pipeline does a pretty decent job with the fast cadence data. I think that that's kind of a very general overview of what happens between the arrival of the photons at the spacecraft and when you click download on your computer to get the data product. Now,
how long does it take between the time an observation occurs and the time the data is available for download?
It depends. So early on, my recollection is that it took a couple of months for the sectors to become available for download. And I think that they've done a pretty good job of speeding that up since then. I can think of a couple where it was only a few weeks, if memory serves. So it's reasonably fast. And the other thing I should add is that there's no proprietary period. It's like if you observe on Hubble, the data will be kept proprietary for a period of time, so no one else gets to see it. With test data, that's not the case, which is a good thing, I think, for science. But if you're like me and you have targets that are being observed by Tess, kind of makes you always looking over your back to make sure no one's about to swoop in and write a paper about something that you looked at, rather that Tess looked at for you. Just a quick administrative thing. Elizabeth and/or Sarah, we're at the hour point now, and I know that the sponsors would like to say something about an hour in. I'm probably about 5 minutes from finishing the PowerPoint. Would it be okay if I just finish that off and then we use the sponsor's message as kind of a natural break?
Yeah, I think that's a good idea, Colin.
Okay, and also give my voice a chance to recover.
So whenever I'll show the video whenever you want me to.
Okay, it'll be really soon, I think.
Okay, just say, so you're saying now or just after you?
I think I'd say in about no more than 5 minutes.
Okay, just give me the heads up and I'll do it.
Thank you.
Thank you.
So the last service I'd like to point out is called Tess Cut. So this is where you can just provide the coordinates or the target that you're interested in. And with the full frame data, you heard earlier how many pixels are involved with each full frame. The file sizes are absolutely enormous. So a more practical approach, rather than just downloading each of those full frames, is to cut out a portion that you're interested in, and then you can work with that. So this is a service that will let you do that, again, without needing any Python or any programming skills. It's really as simple as just entering coordinates or the target. You specify how many pixels you want in each direction. And then if a target was observed in multiple sectors, you could choose which one. So that'll be updated depending upon which target you look at. I'm going to jump back now to the PowerPoint. So any questions on those three resources?
I have one that is not obvious, but the Tess uses a lot of acronyms for names. Is there a place to find a glossary of those names like TIC and TOI and so forth, and what the distinction is?
Yes, there's a very long and detailed observing manual for Tess, but as I recall, that has an entire section dedicated to just the acronyms. So there's a lot of supplementary material that I'll provide after the workshop. So these slides, a couple of short summaries I've prepared, and I'll also include that in those materials. And you said that was kind of a something that wasn't obvious. You're right. I'm glad you mentioned it, because that's exactly the kind of thing that it's very easy for me to overlook. And it's also helpful to have that kind of resource. So thank you for mentioning that. So we're going to start to pivot now towards Lightkurve. So I'll just say a few words about that. And then I'll let our sponsors have their message. And then after that, we can actually start using Lightkurve. So just kind of the rationale for why I thought it would be the appropriate tool for this workshop. So it's open source, which is, I think it's always a good thing because it encourages development. It means it's going to be free. And it's also better just from the standpoint of security, although that's kind of more of a general software concern rather than something that's specific to science analysis. And the other thing that's really striking about Lightkurve is that they actually say that one of their goals, one of their explicit goals, is to lower the barriers to entry for amateur astronomers, among other groups. So it's not that it's aimed specifically at amateurs, but they realized that there was a possibility it could be suitable for advanced amateur astronomers. And compared to a lot of the other Python modules that or Python packages that I've used, I do think that it has a somewhat gentler learning curve. There's some that you really need to have quite a bit of Python under your belt to work with. Lightkurve, you can get by with knowing little to no Python initially. And my hope is kind of that people will look at this, and I know that it's not going to be for everybody. So for those of you who fall into that camp, I feel for you, and hang in there. I'll try to make it as painless as possible. But there's also another segment of the members who are present today who I'm hoping will look at this and think, wow, that wasn't that bad. I can do this. I'd like to know more. And even if they don't want to stick with Lightkurve, maybe it will encourage them to develop other Python-based software for the AAVSO. So the AAVSO president, Gordon Myers, is an advanced amateur astronomer who knows how to code in Python. And some of you may have used his TG software to calculate your transform coefficients for photometry. And I think it would be a wonderful thing if more amateur astronomers were involved with that. So I'm kind of hoping a few of you might take the bait there. I'd also like to underscore that although I've chosen Lightkurve for this particular workshop, it's not the only option out there. And I do think that there are tools that might be more suitable for certain types of scientific work. So we'll probably talk a little bit about that later. I don't want to dwell on the details too much right now, but I don't want to be boxing you in at the same time. So Elizabeth, I think this would be a logical segue, I think, to begin the message from the sponsors. And then after that, we will we'll jump into the notebook that I circulated earlier.
Sarah's going to run the video now, Colin.
Thank you.
Sure.
Is. Sorry, I have no choice. No, because it's show.
Hello everyone, my name is Qiu Hongyun and I am CEO of Pulsators CCD. Let me introduce our company and products in this conference. Pulsators designs the astronomy cameras for almost 20 years, and we supply both for amateur astronomy camera and also for professional astronomy camera. We have both CCD camera and CMOS, and now most of our camera is CMOS cameras. Because many CCD sensors has discontinuous, so now we most of our cameras are the CMOS cameras. I hope that I was getting many questions about how to find the suitable cameras for photometry. In this conference, I'm proud to introduce some of our new monochrome CMOS cameras. This camera is using the Sony 3.76 micron pixel size sensors. And this sensor is backlit, and also there are 16-bit AD converters. Basically, this camera is very suitable for photometric using. There is totally 4 models of these servers: Pulsar 600, Pulsar 200, 16.8, Pulsar 411, and Pulsar 461. I think the most important thing for photometry is the familiarity of the sensor. So we did some tests for these cameras, and this curve is the Pulsar 600. We can say it's a very large linear range from up to 16.5 25K electrons. And I also test, we also test another model, which we have 411, and this is the test results. And this result is also very good, which shows a good performance of the universe of these cameras. And the full view of this camera is very good, even for the 16, even for 74 microns. The pixel is not very big, but even for this small pixels, it has very large full view. For 600, we have measured about 16K electrons. And for read downloads, this camera is also very good. It is in high beam, you can get about 1 electron read downloads, and in noise, it can get 3.5 electrons. And for the very big full wheel, the 18K full wheel, it can get 6 electrons. The most popular camera of this series is Virtual 600. This camera is full format. We made this camera about last year. The October we have sent the first cameras to the market, and it is 16 bits, 16 megapixels, back-emitted sensors. And also this camera is zero anti-flow. So even you make every dynamics per time times 600 seconds, you cannot see any amplitude on the image. And also they have no RPI reading, so it is very good. We did a special timing to clear the reading between frames, so it has no RPI readings. The upcoming product is Virtual 268. This camera is APS-C format. It should be cheaper than Virtual 600. The Virtual 600 is about $4,000 to $5,000, and the professional version is $8,000. This Virtual 216 is maybe more than $2,000. In this design, we have a very special design for the to get every big full wheel. This technology is we have the this is like universal technology that we have. In Sony's case, it is only 15K full wheel, but our camera can get 18K full wheel. For Virtual 600, we can supply different models, and the short focus version. You can get about 7 millimeters focus. And also we can supply the waterproofing customer-rated version to reduce the fans, the vibration, and for the hot air turbulence to reduce get better things, especially for the ISA systems. This is some nice features of our user use Virtual 600. Okay, this is the tip I want to promotion. Thank you very much, and we are very glad to start the AAVSO conference in this year.
Okay, take it away, Colin.
Okay, thank you. So at this point, I would like to start moving towards Lightkurve. And there's going to be a bit of a change, I think, kind of in the experience of the workshop at this point, because at this point, it's mostly been me talking and people asking some questions, some very good questions, if I might say. I'd like to make it more interactive now. And so I'm hoping that each of you will be able to follow along on your own computers. It's not absolutely essential that you do it, but I would encourage you to, because it's a lot more fun when you actually get to work with the data. And it's just the best way to build up experience. So I will resume my screen share. Bear with me for just one moment. And if you could all go ahead and load the notebook that I sent earlier today. So let me remind you how to do that. So I sent you not a couple weeks ago, about a week ago, a test notebook that I asked you to run. I think the easiest solution would be if you take the notebook that I sent you before the workshop today. If you take that and you just save it in the same folder as the test notebook, and you launch it in the exact same way. So if you're running Windows, I would recommend using the Anaconda prompt. So you open that up and you type Jupyter Notebook as you did previously. If you're using Linux or Mac, you would open up a terminal and type Jupyter Notebook. When you do that, a screen similar to this will pop up where it's showing a file directory on your computer. So this will just open up as a tab inside your default web browser. And all that I've done is open up the notebook that I sent earlier. And so if you do it successfully, you should see something that looks like this. Now at this point, I'm going to reiterate my encouragement earlier that that you should feel free to jump in at any point, especially if I'm moving too quickly. So I'm going to give you all about another 30 to 45 seconds just to make sure everyone has had a chance to do this. And if any of you are lost, let me just show you on my screen if you need like a visual reminder of what this would look like. Ignore this. Okay, this is the part that that you would pay attention to if you need that reminder. So on the terminal, you just type Jupyter Notebook. And again, Windows, you would do this in Anaconda prompt, and you run it. And then it's a little bit different on my computer, but that's all that you would need to do to open it up. And I'm going to close it simply because I already have it running and I don't want to have two running at the same time. So I'll go back to the notebook. I'm going to assume at this point that you've all been able to open it. If again, assuming you're interested in trying to do this on your own computer, it's not absolutely essential that you do. Certainly at this point in the workshop, if you're more interested just in following along and seeing what it, you just want to see what it looks like on someone else's computer, that's totally fine. So a couple of words about this format. So you all saw that screencast that I circulated last week. And I said that this was a Jupyter notebook format, which I don't expect anyone to be familiar with because it's kind of unusual. Even if you've already previously done coding before, it's a really novel way, I think, of writing computer code. And the major benefit of it is that your code can actually start to look a lot more like a blog post instead of just a huge impenetrable block of code that nobody can understand. It lets you embed just plain text, like this explanatory text that you see on screen. You can put tables, you can put bulleted lists, you can put YouTube videos if you want to, and then you can intersperse computer code in there. And the benefit of this is that you can provide a lot of explanatory information about the code rather than just throwing a lot of code at people. So I'll give you just a very, very quick overview of the architecture of this, because it's probably a little bit weird to see computer code being presented in your web browser. And one thing I would like to be very clear about with this is that even though you're viewing this notebook in your web browser, all of the code is stored locally on your computer. So the idea here is that the web browser is merely providing an interface to communicate the code to the part of your computer that's actually doing the computations. So I don't want you to think that this is automatically being backed up to the cloud or anything like that. It's all being done locally. So you don't necessarily need an internet connection to run a Jupyter notebook unless the code itself needs to talk to the internet. I can answer questions about the particulars of the format later on if you're really interested, but realistically, I don't think anyone signed up for this workshop to learn the ins and outs of Jupyter notebooks. You're here to learn about Tess. So let's dive into this notebook, and I'll work through the explanatory text at the top, and eventually we'll get down to some code. And where there's code, I just want to say, don't focus on the details of it unless you already have a background in Python and you want to see what's going on. One of the many benefits of this approach is that you don't actually have to interact with the code to make this work. And so you can do all kinds of stuff with test data and never have to bother with a single line of code. So let's begin with this.
Hey, Colin.
I hear a question.
Yes. What was the command you typed into the terminal to bring up the screen you have now?
It was Jupyter, Jupyter.
Yep.
Notebook, Notebook.
Okay. I just got the what you sent out last week in my browser when I do that, not what you have on the screen now.
Okay. How about this? Why don't we talk about it at the end of this session?
Great.
I think I know what the issue is. It's just that you didn't save my guess is that you didn't save the file in the right spot.
Okay.
So that'll be a quick fix. If you just follow my screen for now, the second half of the session is where we'll really be doing the heavy lifting.
Great. Okay. Yep. Thanks.
So if there are technical issues, this is the part of the session to have them. So for those of you who were able to load this notebook successfully, I've listed here at the top a number of targets, and we're not going to get to them all. I wanted to list too many. Just in the off chance that maybe we just burned right through the list of targets. I wanted to make sure that we still had something to look at. But I'll choose a couple of representative targets from the list up here, and I'll just show you how this notebook works, and I'll explain it each step of the way. So I think a logical beginning target might be XZ-SIG, which you might remember from the test notebook that I sent previously. And then I'll also show you Thuban, which is it's the very bright naked eye star that was discovered to be an eclipsing binary from test data. So we can reproduce that result right here and now. But first, XZ-SIG. So if you scroll down a little bit, you'll notice I've divided this notebook up into what I refer to as cell A, cell B, and cell C. And then there's all that explanatory text at the top. But each of these cells is structured so that it performs a specific function. And I've tried to be very clear about that in the explanatory information for each of these cells. So the cell itself refers to this block of code down here that you don't need to worry about unless you really want to see what's happening in there and you know Python. So you'll see that there are instructions for each cell specifically. And here, this particular cell, you need to just tell Python what target you're interested in looking at. And it will then query the Tess archives to see what data products are available. So is there FFI data? Is there 2-minute cadence data? And it will then report back to you and tell you what you can download. So let me show you what this looks like. So I'll scroll down a little bit. All you have to do is click somewhere in the cell. And notice now it's highlighted in green. Simply click the run button here to execute it. And then what will happen is it's going to execute that code and a little box pops up down here. It asks for the name or the coordinates of the target. And I said XZ-SIG. So you can just type that in and hit enter. And then this table down here pops up. So there were a couple of status reports right after I entered in XZ-SIG. But this is the part that we're really interested in, this table down here. So you'll notice that, first of all, XZ-SIG was observed in 5 separate sectors. So test sector 14, 15, 16, 20, and 23. And over here it says description, target pixel files. So if Tess observed a particular target at the 2-minute cadence, the description will show a target pixel file there. If it was FFI data, it would say FFI. And we'll see that later on with some of the other targets, because in fact, most of them are FFI only. There's also another bit of information over here that isn't absolutely critical, but it might be useful if you're looking to collaborate on some of these results. It's the proposal ID. So this particular target was requested by a particular research group. And the proposal ID is what you can use to identify who that was. So elsewhere in this notebook, in fact, if you just scroll down a little bit, when I give a description of what the table is, there's a link here that you can click on it, and it will take you to a list of all the proposals, and you can see who that is. And if you wanted to collaborate with them, that's how you could go about it. So this explanatory text down here, it's only summarizing what I mentioned a moment ago. There's one key point that I want to highlight here. On the next cell, we're going to be choosing which of those observations from that table we want to download. So sectors 14, 15, 16, 20, or 23. And you'll note that there's a number immediately to the left of that 0, 1, 2, 3, 4. We have to take the number that corresponds to the sector that we want. So in this case, if we want sector 14, that's going to be 0. Or if we wanted sector 20, that would be number 3. So in the next cell, I'll use this number here, 0, to tell Python to download sector 14. So cell B, it's all it does is it downloads the data that you desire. And then I'll explain this table when it's necessary. So as with the first cell, you just click anywhere in here, you click run, and it's asking me for the value of the number column from that table. And we decided sector 14, number 0, we'll go with 0. And it asks for something else, a little bit of jargon here. We have to specify a quality threshold for the data. And the options here sound kind of weird. There are 4 of them. You can specify no quality requirement, so that would be none. You can specify default, but then hard and hardest, which aren't particularly self-explanatory. However, up in the explanatory material for this cell, I give you a short summary of what each of those corresponds to. And I would generally recommend hard, which is kind of a conservative cutoff. It will eliminate some good data, but it will generally do a pretty good job of eliminating data that has known issues with it. So there's some test observations that are just, for lack of a better term, they're just really bad. They're just junk. It's rare for test observations to be low quality, but sometimes it happens. Maybe there was a brief pointing issue with the spacecraft, or a cosmic ray hit in a particular image. Whatever the case, you can use this to get rid of the worst of the worst. So in this case, I'm just going to specify hard, which again, that's kind of the default that I recommend. Type in hard, hit enter, and then it will download the data. And by specifying that threshold of hard, it's automatically going to exclude the suspect data from that Lightkurve so that it won't contaminate future analysis. And finally, cell C down here. Now, I've configured mine a little bit differently. So let me explain why. My cell is, I decided to set it up so it would create a finder chart so that you can pick out the variable star in the Tess image. Let me show you what that looks like down here. And I'll explain why I didn't send that software to the workshop in just a moment. So if you run this cell, you'll see this prompt here. So again, just click anywhere in the cell, hit run, and then it's going to ask you what you'd like the file name to be when you save the Lightkurve. So in this case, I suggest something just like xz sig. Then this was sector 14. So it doesn't matter what you call it. I just recommend something that's descriptive and memorable. You hit enter, and then you won't see this prompt in the version that I've sent you, but I'll run it on mine and you can see what it looks like. So you will see this panel down here. So this is what you generated when you did your tests in the past week. So this is the interactive Lightkurve. So I'll start here and then I'll show you the finder chart up there. So there are a number of different things you can do with this panel down here. And the great benefit of it is that like if you wanted to try to do all of this just by writing computer code, it would take a fair amount of effort and quite a few lines of code. Here, all of that is happening behind the scenes and you don't have to worry about the details of it. So in the right-hand side of the frame, you see an image from Tess. So this is one of the frames from the 2-minute Lightkurve of XZ Sig from sector 14. And you'll notice that there are a number of highlighted pixels in it in white. So up here and then down here as well. What's happening is the intensity of each of those pixels is being added together. And then that's what's being represented over in the Lightkurve at left. And so for each frame in the Lightkurve, that's what's happening behind the scenes. And this is just the first image in the sector. But if you click this slider down here and you drag it like this, you can actually see XZ Sig pulsing in the image at right. And as I drag the cursor, you can also see that there's a red line in the Lightkurve, and that's moving along with the cursor. So that's showing the location in the Lightkurve where that frame at the right is. And this is especially useful if you see something weird in your Lightkurve and you're not sure whether it's real or an artifact. Now in this case, this is a pretty well-behaved Lightkurve, and I don't see any obvious artifacts in it. But later on, there are a couple of examples of artifacts where this particular tool is going to be really helpful in spotting them. I should add also that if you're unhappy with the pixels that are being added up to produce the Lightkurve, this is interactive over here. So you can click on those pixels and it will show you an updated Lightkurve in real time for those pixels. Now at this point, I just want to pause briefly because one of you is using an alternative kind of impersonator of this particular tool that I designed myself because of installations that you were installation problems that you were having on your computer, that you couldn't get this running yourself. And then I provided kind of an imitator of this that would at least replicate some of the functionality. For that one person, you should be able to click over here on the image at the right, pixel by pixel, and it should change which pixels are being selected. It's going to be a little bit slow because you're running it through a different interface, and you should also see that slider underneath the Lightkurve. But a lot of the other functions, unfortunately, just aren't there because I didn't have time to try to code them. But for the rest of you, this should be what you see on screen right now. So I'm just going to select a bunch of pixels by click dragging. And a couple other things you can do with this. If you look underneath the Lightkurve, there's a magnifying glass. You can click drag a rectangle over the Lightkurve to zoom in on it. You can really get nice and close to get an idea of what it looks like close up. So the precision of this particular Lightkurve is just exquisite. And then if you want to reset to the default view, you just click this button here. Looks like a couple of arrows going in a circle labeled reset. And we're back to the default view.
Colin?
Yes?
I had a question because you just selected multiple pixels. I was wondering if you could give some guidance to people on how to figure out which pixels to select, how many to select, etc. I know that's a hard question.
Yeah, that's, I think for that, it's the sort of judgment question that for which there's no right or wrong answer. So I know that I can remember one time when I wrote a paper and the referee asked for further justification about my choice of pixels. It's really driven, I think, by considerations of blending, and I think the other thing I would suggest doing in a lot of cases is just going pixel by pixel sometimes and seeing if at what point the quality of the light curve really begins to degrade. So there's this trade-off here that XZ-SIG's light is spread across a huge number of pixels in there. You can see this when I move through the frames, that most of the pixels in this image contain some signal from XZ-SIG. But the ones like way up here, you can still see those pulsations there, but notice the amplitude. So the units here are just electrons per second. So electrons generated on the detector by photons from the source. And there aren't many. It's an amplitude of a couple of electrons per second compared to over 3,000 towards the center of XZ-SIG's image. And again, up here where you're getting towards the halo of XZ-SIG, it's dipping down even a little bit below zero because of calibration issues with the data. So the pixels, the long story short, is that up here, these pixels are contributing very little information about XZ-SIG, but they are contributing noise. So it is a bit of a trade-off, just selecting different pixels and seeing what you get. And I think that it's difficult to have an objective criterion for what the best selection might be. The default is very often pretty reasonable, but you should feel free to deviate from that if you think you can find a better ensemble of pixels to choose.
So I just have two quick follow-ups to that. I'm assuming, of course, that we would always want to choose connected pixels and not leave an island of pixels here and there.
Actually, as reasonable as that sounds, when we get to Thuban, that's not going to be the case. There's no reason in advance that you couldn't do that. And when we get to Thuban, so that's the Alpha Draconis, the very bright eclipsing binary, you'll see why it's actually advantageous in some instances to select discontinuous groups of pixels.
And then the other question I have is, can you remind us again of what the angular resolution of Tess is in terms of pixels?
Each pixel subtends 21 arc seconds.
And right, and I what I'm trying to get a sense for is what is the actual limiting diffraction limit of Tess?
So the diffraction limit would be significantly better than that. So it's about a 4-inch telescope. But the problem is it's nowhere even close to that. So the statistic that's given in the Tess literature is that I believe 90% of the energy received from a particular source will be enclosed within a 4 square pixel grid, so 2 pixels by 2 pixels. So it's not like it's tightly focused or anything. The light is significantly spread out. So the diffraction limit, although it exists theoretically, Tess doesn't come anywhere close to it.
Okay. So a 2 by 2 pixel seems like not a rule to live by, but perhaps a starting point.
Yeah, and keep in mind, I think that perhaps you could summarize the goal of pixel selection as trying to maximize the signal to noise ratio of the light curve. And so that's going to be driven by how bright the source is and how heavily blended it is with other sources. So if XZ-SIG were the only source in here, you'd be well justified in selecting lots and lots of pixels. But let's say that it was right next to an even brighter star. There you might have to select only a few pixels because for the most part it would be heavily blended. And we'll see examples of this later on in the workshop. Were there any other questions about this particular light curve? Because if not, I'll show you what the finder chart looks like. So this particular, the software for this was developed by Ken Miguel at NASA Ames. He responded to a request of mine on GitHub. And he was wonderful about going out of his way to respond to all of my crazy requests for the software. But the reason I decided not to circulate it to everybody yet is simply because I figure you're going to have enough trouble just getting Lightkurve up and running. And I didn't want to throw more installation requirements at you. So my plan is just to show you the Finder chart on my computer via the screen share. And for those of you who aren't scared away by Tess after the workshop, I'd be happy to explain to you how to install this. It's not difficult. It's just that, you know, I don't want to just keep asking you to do one thing after the other in preparation for the workshop. Just by installing Lightkurve or trying to, you've gone above and beyond. In his Finder chart, though, a couple things I'll point out that make it really helpful. So it's showing you the equatorial grid, but more importantly, it gives you this blue grid, and those squares represent the pixels in the image below. So you can directly match up this Finder chart with the actual Tess image. And the nice thing about the Finder chart is it's a digitized sky survey frame, so it has very good angular resolution. And it gives you a sense of just how bad the blending is with Tess. You can see this bright star up here, right on the edge of the frame, and it's spread across a number of pixels. And same thing for this star that's off frame. You can still see it blending in over here. And then a bright star down here is starting to overlap a little bit with XZ Sig in the middle. And there's some fainter stars closer to the target, represented with the green X, that are just hopelessly lost with XZ Sig. So I think it's, if you want to stick with this particular workflow, I do think that the Finder chart is helpful, especially when you start to move towards fainter objects that aren't as obvious when you just look at the raw frame.
What are the red squares? What does that indicate?
So those were the default pixels that were selected for summation into the Lightkurve.
Okay, so the Lightkurve that you the first result of Lightkurve is based on those pixels, not the entire field of view.
Correct. So
okay.
yes, that's an important point. That with the 2-minute targets, there's a predefined aperture, and there is an algorithm that generally does a pretty reasonable job with it. You should still feel free to experiment with other apertures. So that's, if I haven't defined that term previously in this context, aperture is just what we call the selection of pixels that you're adding together. So if the pipeline aperture, if you don't trust it or you think it could be improved, you should still give it a try. But I generally consider the pipeline to be a pretty good starting point. With full frame data, it's a whole nother story because there is no predefined aperture. So there it can be a little bit more of an adventure.
So it looks like it might be a good idea to look whether there are other variable stars very close to the target, right? Because in the end, you will see a combination of the periods, right?
Exactly. And in fact, with some of the targets that I've picked out, that starts to become an issue where there's blending. And if you look up here, I think that perhaps the green is blending in a little bit with the background, but you can see if Tess's, if the frame that we had below was just a little bit bigger, it would actually encompass another variable star as well. And up here in all the readout from Ken's software, he gives here a table with information for that second source. So you can see that it's a high amplitude delta Scuti star with a period of 0.089 days. But it's also pretty faint, 19th magnitude, so it's unlikely that it would be a significant source in Tess.
So I don't know if you can hear me. This is Joyce Gusek. When I try to use the reset button in my Jupyter notebook, it just blanks out my Lightkurve and highlights all the pixels in the sector. That must be a problem with my machine somehow, right?
No, I think that's just one of the quirks of this. Try reselecting the pixels in your frame. Trying to remember the exact sequence that I have to do to get that behavior, but I've seen it before on my machine.
Okay.
I think it falls under the category of a bug that the developers know about, and you know, they'll try to eliminate it at some point. But there's so many different things that they're working on right now that I'm not sure that that one's at the top of their list, even though I grant you it's pretty annoying.
Okay, thanks.
Of course. Were there any other questions? Because if not, what I'll do before we break for an hour is I'll just run through the Lightkurve of Thuban. Okay, let me jump to that. So if you're following along on your own computer, jump back up to cell A and run it. And when it asks you for the name of the target, Thuban, Thuban. You can see, as with XZ-SIG, it was observed in 5 separate sectors. And once you've done that, I'm just going to take the very first sector so that I'll be entering in 0 down here. So cell B, run it. So from the table above, we know it's 0. We'll go with the hard quality mask. And you can see it's been downloaded to my machine. Now scrolling down to the final cell, just click in there somewhere. I'll skip the Finder chart here because even though I can be bad with star hopping, even I can spot a second magnitude star when Tess looks at it. So this looks pretty crazy, I think. But this is also kind of a classic example of where it's advantageous to select a discontinuous group of pixels. So the core of Thuban there is pretty saturated. But if you select off to the side, the halo of the star is not. I'm also going to try over here as well. And I'm wondering if I might have chosen a sector in which it doesn't eclipse. Oh no, I stand corrected. So there are a lot of, you'll notice there are a ton of pixels in this image over here. And it doesn't really matter too much the exact selection that you make, just as long as you select pixels that aren't in that saturated core there. And you know, we could really fine tune this, but I know the lunch break is coming up for those of us in the US, or those of you who are in Europe. It's probably a little bit closer to dinner. And you probably don't want to run into that time too much. But here's the Lightkurve I get from that selection of pixels. And I'm just going to click this tool here, the 4 arrows. I'm going to go down a little bit, and you can see right here, there's a very nice eclipse. You don't see it initially just because of the y-axis limits that the software automatically decided. You can see it goes way down, relatively speaking. I mean, it's still a second magnitude star and it doesn't fade too dramatically, but it's very obvious in Tess, even though, as you can see from the image, the core of the star is pretty heavily saturated. Now I should add that the Lightkurve you're getting over on the left. It's not like it's the end product or anything. So here it's a little bit annoying that I have to scroll down like that to get all the way to the bottom of the eclipse. But the main point of this tool is just that you're able to get a quick preview of the light curve. And if you see some suspicious feature in it, you can then inspect the resulting images to see if there's an artifact that might explain it, which is something I think those of you who do CCD photometry on your own, you're probably accustomed to doing something like that. If you have a light curve and it has a weird flare or weird dip in it, one of the first things you probably would do is inspect the original frames to see if there was something that might explain it just from an artifact. And with this particular workflow, you can do the exact same thing. So I think it's kind of an intuitive way for amateur astronomers to start to enter into the realm of Tess analysis rather than just tackling this from writing computer code. So I'm 1 minute and 10 seconds into the break. So I'd be happy to take questions now, but if some of you just want to get away for that hour that we have off, I certainly wouldn't fault you, and I'll see you when we pick up again. And there was one person I promised tech support to, so I'll stay on for that as well.
What's the time format? Is it JD or what, as far as the x-axis?
So Tess normally reports its observations in what's known as BTJD. So I think most amateurs are probably familiar with JD, Julian date. I don't know how familiar amateur astronomers are generally with BJD, which is barycentric Julian date. That's where you correct the arrival times of the photons for Earth's motion around the center of mass of the solar system. The idea there is that if you don't apply that correction, the arrival times of photons will depend on where Earth is in its orbit, and also with Tess, where it is in its own orbit. And so what we do is we calculate the arrival times of photons at the center of mass of the solar system, which we can treat as being stationary, non-accelerating. With Tess observations, that correction is automatically applied. Furthermore, we use, this is a little bit of jargon, so I don't expect it to be relevant to everyone here, but we use the TDB time scale, barycentric dynamical time, essentially just a continuous time standard. So you can think of it as kind of analogous to putting an atomic clock at the center of mass of the solar system and timing photons that way. So all the corrections that amateur astronomers might need to apply normally, it's already been taken care of here. And one final thing with BTJD is just that normally there's a constant number subtracted from it just to make the numbers smaller. In this case, that number is given right here in the Lightkurve, 245, 7,000. So if you take BJD, you subtract 245, 7,000, you have the BTJD. It's probably more information than most people put into.
But it is the BJD TDB.
Correct.
Okay, thank you.
Colin, was there a shortcut to scroll back up to the top of the curve? No?
You mean when I was scrolling down to the minimum of the eclipse and then going back up
again? Yes.
Yeah, probably just if you see where my cursor is, you hit that reset button, and then the light curve goes blank, which was the issue that was reported just a minute ago. So I'll address that by just selecting another pixel, and that should cause it to come back.
Yep, the reset worked.
So just this time minus 24,000, yeah, 200 whatever is basically essentially close to the modified Julian day minus 57,000 as well for those people who use that process. There's a half day offset.
That's a good way of putting it. I'm glad you thought of that.
It's a half day. It's a half day offset, but it's close enough.
Colin, just a real quick question, and I can take this offline or talk to someone else, but I never received the notebook. Is there a place I can go to download that?
Yeah, I'll email it to you. Sorry, it's not telling me who's talking.
We'll send it, Bob. We'll send it, Colin. We'll send it to Bob.
Thanks. Thanks, Elizabeth.
You can send him the version you sent him to me. Here's Matthias from Germany, because it's at least showing. I mean, it's hard to work in that web application the same way you can do really if you have downloaded it, but at least you can quickly see everything.
Yeah, the web application, I have to underscore, it was kind of a last ditch effort that someone who's better at web design and programming than I am could probably have come up with something pretty impressive. I just wanted to make sure that you'd be able to follow along on your own, and at least have some level of functionality.
No, it's great for the training, definitely. Yeah.
And certainly, my offer stands that after the workshop, once we both have enough time, we can just sit down and we can troubleshoot the installation, because having the local installation is vastly superior.
Sure.
And perhaps unsurprisingly, it turns out that people who program for NASA are a lot better at programming than I am.
Colin?
Yes?
Thank you for this wonderful presentation and all the Jupyter Notebook files that we can use from home. I have a question with regards to the proceeding. I tried to save the Lightkurve, but in actual fact, it saves the Jupyter Notebook. What we've kind of looked at in this platform. Is there the possibility to save it and be used by other software that we're perhaps more accustomed to?
Yes, and I'm thankful that you thought of asking that question, because I completely forgot to point that out. If you look at this widget here on my screen, look at the green button underneath it, Save Lightkurve. If you just click that, that will save, you can see right there, saved file thuban.fits. So if I go back now and I look in the directory where I have this notebook, there's a lot of stuff that isn't relevant here. But here's, in this line right here, I'll highlight it. So it's the top of those two, but thuban.fits, created just seconds ago. And that's what will be loading into VStar later on. So to answer your question, just use the Save Lightkurve button down there once you've identified a Lightkurve that you're happy with.
Colin, are you going to also, I don't know if the cell is here, to save it in a CSV format? I know that's one of the options you used to have.
Yeah, so that was an ad hoc thing that I did. I could show people how to do that if they wanted to. But I decided for the workshop it's probably best to try to the maximum extent possible, try to standardize the workflow. So, so that fits file can be loaded directly into VStar. For those of you who use a different software platform for period analysis, like maybe say Peranso, I can supply code that will take that fits file and convert it into a format that you could then load into Peranso or whatever software you prefer.
Colin, when I click into a cell and click run, nothing happens. I can't, there's nothing where I could input anything.
Okay, let me suggest probably the most logical starting point. If you go up to the kernel menu, let's just tell it to forget what it's doing and just start over again. Because sometimes what might happen is it'll freeze up for some reason. So click kernel.
And restart.
And then you'll get this message here, restart kernel. Do you want to do this, all variables will be lost. Just click
Okay.
Start. And that kind of
Okay.
clears the decks and it lets you start over again. And if that didn't work, I have other possibilities as well.
Yeah, that
also
nothing happened.
Okay, we can also do a screen share, although before we do that, my understanding is that this will probably be posted on YouTube or something after the fact. I realize not everyone's probably going to want to do a screen share and then have it be on YouTube, just for the privacy considerations. So let me show you a couple of other possibilities that it could be. And then if that's still an issue, we could continue to troubleshoot it. So it's possible that maybe your cell looks something like this.
No,
So your code does look like
it looks like that.
Okay.
I'm having the same issue. Initially, it was working fine, and now it does nothing when you run one of the cells.
Interesting.
I'm having a similar problem. This is Joyce. I tried just quitting everything and starting over, and I'm having trouble with it saying, giving me warning messages about files that already exist. And this is Thuban. And when I try to run cell C, it gives me a bunch of error messages about the Lightkurve. It won't let me, it says it won't save it in TPF format while I'm not trying to ask it to do that. So I don't know what it's complaining about. It's done
I'm
that
not
twice
getting
now.
any error messages. Nothing's happening.
Wow. Yes, it's our unlucky day then. I have just all these error messages.
Sorry. Yep.
Oh, go ahead.
Yeah, I have a problem too, but perhaps it's the same. I don't know why, but the server, the local host, is listening at 8890 instead of 8888. And
Okay.
if I
Yeah, for those of you who have that problem, so this would be down in cell C when you plot the Lightkurve. You jump all the way down there. Oops. And then I'll circle back to the other issue because I can think of a couple more things that we should look at. But when you're plotting the Lightkurve, okay, so the very bottom of cell C, if you look at the final line there, notebook URL, it's this value right here. Notice it's got that 4-digit port number. And you want to make sure that that agrees with whatever is up here in your URL. So in my case, it's still the default value, 8888. And so that's good. But if your value disagrees, so if it's 8890, change this to 8890. The reason you get that message, and it's probably the single most common issue with this particular tool, and I kind of wish that there were a better, an automatic solution for it. It's that you're probably running multiple Jupyter notebooks at the same time. So each time you start a new one, that port number, so the 4-digit number in your URL, it goes up by 1. And so what will happen is that if there's a disagreement there, like this software is going to look at 8888, and if the notebook is if it has a different port number, they won't be able to talk to one another. As for the before I circle back, did that clear up your problem?
Yes, mine is fixed.
Okay.
It didn't clear up my problem. I had 8888 already at the top and the bottom. I'm trying to just quit again and start over to see if it helped.
Yeah, I can think of a few solutions here. So one thing I'll suggest, I've gone back to this other tab on my screen where it's showing the file directory. Right next to the notebook that I'm running, it says running. Can you confirm that it shows the same thing for your notebook?
Yes, well, let me take a look at that. I see what you're saying. I have to, how do I get to that screen? Go back
So
to
this,
file?
let's see. So it would have been the screen that popped up when you started everything. Otherwise,
Right.
let me see if there's
It
another way.
should just be the other tab, the second tab up top.
Okay, let me take a look. Yes, it says running.
Yeah, good point, Gordon.
It does, it says running.
It does say running.
Yes.
Interesting.
And let me,
When I've had this trouble, I've gone back to the fundamentals and rebooted my computer and started up. So nothing else works during the break, I would do that.
What I would suggest then, maybe in lieu of that, I mean, certainly restarting the computer doesn't hurt, but it's probably a little bit annoying when you're
Yeah, no, I agree.
and all that. What you could do is close your notebook. So, for example, on my screen right now, you can just hit quit, and then what's your operating system?
it's a Mac. Mojave.
Okay, then you could just kill the terminal where you started the notebook. So
I did
you'll
those
just-
things 3 times already.
Already, wow.
I think restarting my computer sounds like a good plan. I'll do that on the break.
Joyce,
So
before you
out of
restart
curiosity, did you run into any of these problems with a trial notebook that I circulated?
No, and I did fine with XZ-Sig. It was just when I started this new star Thuban that I'm having this trouble.
So before restarting the
I
computer,
mean, if I were going to pick a naked eye star that was going to wreak havoc on computers like this, I should have picked Algol, the demon star, since it's having that effect on everyone's computers. The only thing that maybe I can think of is that for some reason the dimensions of the file, the dimensions of the image might have messed things up, that it's a larger file size and maybe there was an issue with the download, but I'm really grasping at straws with that.
Right.
My suggestion might be if XZ-Sig worked a few minutes ago,
Right.
just launch the notebook again and try that again.
Mhm.
And if you wanted some peace of mind, you could try one of the other stars from that list to see
Yes.
if that works as well.
Okay. All right. I'll play around with that. I don't give up very easily, so it's probably
No,
some.
I can tell, and I'm glad that you've stuck with it, because I remember how I was when I first learned Python, and I can remember some very dark thoughts crossing my mind when
It usually takes me about 3 days. You know, the first day I have problems, and the second day I try it again and I get through a few more problems, and the third day I get through a few more. So you just have to keep coming back at it, trying again. So
there
yeah,
may be another issue.
Pardon me?
There may be an issue in terms of when people actually updated their software, and perhaps there was a minor bug in between updates. So whenever I run into a Python issue where something was working before and it's not working now, I go ahead and just try to see if I can update my my library. So doing the Conda install that Colin told us to do. If you do it again, it will update things if they have been updated. And so perhaps there was a bug report or something like that. So
it's possible, but with Lightkurve, I'm not aware of any new developments in the past week since it was downloaded. I mean, I wouldn't rule it out, and it's certainly a logical argument. It would just
it's the dependencies.
It's
my
possible.
Conda is like, yeah, mine is about a month old now. It was from early September when I downloaded Lightkurve. So
that would be a definite possibility then, because I'm thinking in terms of most people having downloaded it probably about a week ago. But if you installed it prior to that, then certainly it's possible that there was an issue with the dependency.
Those are all good suggestions. Thanks.
Colin, may I talk, please?
Oh, yes, please do.
Yeah, I had the same problem with everyone else. Like my data in XZ-Sig worked, but not in Tuban. It gives an error of not downloading. I guess as I understand it, it's not downloading the data. And as you suggested to Joyce to try the exec cyc again, and I tried it, and it's working now. I think there's something in downloading Tuban data.
That's interesting to know. Thank you.
Yeah,
I'll have to play with this on my end. First of all, I want to see if I can try to replicate it. Those of you who already have some experience with Python, if you were so inclined, what you could do is make a note of your version of Lightkurve, and we could compare versions and see whether maybe someone is using an older version. We could also look at some of the versions, the dependencies, and then the goal here would be to report it to the Lightkurve developers if, in fact, this is a widespread problem, and it seems like it might be. Now, for my part, I don't remember the last time I updated Lightkurve, at least the version that I'm using now. So I did install in a different environment the most recent version, but I'm not using it at this moment. So it's entirely possible that I'm just using a version that works with it because of some fortunate coincidence with the dependencies, and then people with newer versions are not. Those of you who had issues with Thuban, if maybe you could try st-try. It's reassuring to know that xzsig works. Thuban is the only strangely shaped file that we'll be working with. So at least if st-try works, the rest of the observation should be okay. And I'm sorry, there was a question going back about half an hour ago, and I'm sorry it kind of fell back on the back burner. I just got distracted. There was a question about not being able to view this particular notebook. I didn't see who asked it though.
Oh yes, okay. This is Bob Crumrine, and I did figure it out. Now I'm and I got it to work all the way through xzsig, and now I'm trying to try Thuban. And
this will be interesting. Does Thuban freeze up your computer as well?
It doesn't freeze it up. I got to where it says downloading data set. This might take several seconds. And what do I do next?
When
I got stuck on that also.
Interesting.
Where
So
it says it's downloading data set. It may take several minutes and nothing happens after that.
Okay, now after quite a while, it did say now download, so data set has been downloaded and saved in and then what happens next? I forgot. Then
so just keep going. Go through the cells in order. So that was the end of cell B. Just drop down to cell C and run it.
Yeah, cell C.
So it sounds like the bottleneck is with downloading the Thuban observation.
And so I clicked run for cell C, and now it's got the text at the end highlighted, but I don't see any Lightkurve like I did for xzsig.
When you say highlighted, if you can still see my screen share, do you mean? Oops, sorry, I didn't go down far enough.
Just click that, and then I clicked that. I said, "Oh, I never got the what file do you want?"
And
hold on, let me try that run.
And I forgot I restarted mine, so I have to rerun it to get back there. I'll do Thuban again and see if I can reproduce this issue that everyone else is having. Excuse me. I might have been immune to it because I'd previously looked at Thuban, and that meant that Lightkurve could just use the copy it had already stored on my computer. So it didn't have to go through the process of downloading it a second time. So let me download an observation I haven't looked at.
Excuse me, Colin?
Yes?
This is Elizabeth. For those people who are not having an issue, should we just have people go into the break? Is there anything you wanted to say before we wrap this morning sessions? Because we're supposed to start again in 35 minutes.
Yes, and I hope no one was still waiting for that. If you were, I do apologize. At this point, I'm just helping people troubleshoot issues on their computers. And if you're not waiting for tech support, enjoy the break. We'll reconvene in 35 minutes.
Right. So we'll be. Thank you, Colin. We'll be back at 1700 UT or 1700 UT. So in 35 minutes. Thank you. Thanks, Colin.
Thank you, Elizabeth.
Colin, I wanted to report that ST-Try works for me, even though Thuban didn't. ST-Try asked me for some other information about how many pixels in the X and Y direction I wanted to look at.
Because they're getting a little ahead of, I guess I'm getting a little ahead of myself. The reason for that is that it's a full frame image and not one of those nice 2-minute observations.
Right. Yes.
So with full frame, you have the option of choosing how many pixels you want in any direction. And actually, those of you who can still see my screen share, look at what happened to me when I tried to download a new sector of Thuban. Kind of stuck here. So I think that part of the reason I was able to do it successfully is simply because I was able to use a previously downloaded version, and I didn't have to wait like this for it to download. With ST-Try, what you described is correct, and there are a couple of other wrinkles with the FFI data that I'll cover when we reconvene. But it's kind of a fun Lightkurve. And when Thuban is done over here, I will pull up ST-Try along with a finder chart because there's a nice surprise tucked in that frame. Out of curiosity, what were the dimensions that you chose for the pixels?
I get no data found for ST-Try.
Interesting. Let me take a peek in just a second.
I tried the ST-Try.
Right now I've got, I'm sorry?
ST-Try worked for me also, and I chose randomly 5 pixels in X and Y axis, and it gives a graph.
With full frame, I might suggest 15. So 5, I think, would still work. 15 is a little bit better just because it's going to give you more of an idea of what the sky background is doing. So one of the demonstrations I'll have when we reconvene is just what the sky background can do to an observation if something crazy happens. So this is on my screen right now. I've got the most recent observation of Thuban, and it did take a long time for it to download, but once it did, it seems to be working normally, including, you can even see the eclipse right there. My guess is that the reason for the bottleneck is just because there's so many new pixels that have to be downloaded that as I eyeball this looks like it's about 40 by 40 pixels. So you're talking about 1600 pixels per frame. And that's going to add up to a fairly substantial file size. So let me do ST-Try right now. So if you could take a peek at my screen and then just let me know at any point if my input is different than yours. So st try. So it does some searching. It does report no data found up here, but that's just because it wasn't able to locate any 2-minute cadence. And once it reaches that conclusion, that's when it checks for FFI data. And then down here at the very bottom, we have this table. The following FFI data sets are available for download. And you can see that there's a single one, Tess sector 18. Does that differ at all from what you had on your screen?
That's identical to mine, and I was able to get the graphs, so.
Same with me.
Excellent. I just wanted to be sure.
Okay, yes, I see sector 18 now.
And let me just do this on my computer so that you can also see the Finder chart, and you can pick out the surprise that's in there. So again, scrolling down all the way, there's just so much explanatory text in this that makes it seem a lot more bloated than it actually is. So with Ken's Finder chart software, recall that variable stars are indicated with green X's. The target is also circled in yellow. Check this out up here. So just peeking at the summary up here from VSX, you can see that the target has a period of just under a half day, but the other one has an even shorter period. It's also bright, and it's an over contact binary. So it's something that really should look pretty variable in Tess. And if you just scroll through the frames really quickly, you can actually see both of the stars varying very rapidly. And if you choose an aperture that encompasses the other star, you can get its light curve as well. Oops. And then this is back to the original star. So I wouldn't dwell too much on ST try just yet. It's one that I'll point out to the whole group when we reconvene. I'll probably also cover, I'd like to, certainly this one right here, linear 201, and I'd like to get to V808 Origi as well, time permitting. But I want to make sure that we also leave time for the analysis portion. It's amazing when you're trying to plan these workshops in advance. You think you've got 4 hours and you have no idea how you're going to get through it all, and then you actually sit down to do it, and you realize you need a lot more time than that.
Should we let you take a break?
I'm happy to answer any other questions that people might have. Otherwise, I probably will take a break, and hopefully my voice will be back in time for the next session.
Hello, can you hear me?
I can, yes.
Oh, okay. I've been accidentally muted all this time. I have a quick question about Thuban. I didn't have any, it took a little longer to download Thuban, but I didn't have any real problem with it. And I've been messing around with selecting pixels. And my question is, if I have more pixels than I want, how do I get rid of some of them?
You can, if you hold down the Shift key, you can start to click on the selected pixels, and that will deselect them. If you want to deselect a large number of pixels simultaneously, you can hold down the Shift key and do a drag click and select multiple pixels that way.
Okay, that doesn't work for me. For some reason, I only select additional pixels by shifting. This is a Mac. And I've tried Command as well.
odd. Let me pull it up again on my computer. Actually, I don't need to do Thuban for this. This is just a general question.
Anything will be fine.
Yeah. So I'm going to select here just a huge range of pixels. And then if I, looks like I need, let me rerun this because I forgot I started to run the other cell and I confused it.
Well, I think you've already answered my question, which is that this is a Mac problem. And I'll see if I can figure out a workaround.
Nancy, can you hit reset?
I should let you you mean in the pixel data frame?
Yeah,
that selects everything in the picture.
The reset does?
Yeah.
Wow. Okay.
Yeah, right. Wow is right.
Nancy, that's the same problem I have on the Mac too, and I can't do what you just said either.
Ironic seeing that that my experience, the people who developed the software seem to always be using Macs. Think that they wouldn't be having these problems. So I'm just,
it could be a function of the OS too.
I think it might have more to do with versioning of the software, and that would be my biggest guess, is that there's some version issue that you have either with the software itself or one of the packages that is causing the issue. 9 times out of 10, if you have an issue like that where it works on some places and doesn't work on others, that's the reason.
So
which software do you mean?
So for instance, this package is this part of the Lightkurve package?
it is, yes.
Right, so most likely what they have is they have implemented some sort of GUI library or GUI module to make this work, something like GTK or...
It's the Bokeh library.
Right, and so if you have an older version of that or a newer version of that that has a slightly different thing, then it can break stuff, and it's not always backwards compatible. If they're not very careful about what they do and what they say is allowed, then that can be an issue. So the thing to do would be to see what versions of the software you have on your computer, like what versions of each package you have and what they technically support.
I'm going through right now and just confirming that shift clicking on individual pixels deselects them. Although for some reason, this one right here doesn't want to go away. There it goes. Yeah, I'm just kind of surprised that a Mac would be having that issue, but certainly it's possible that there was just an update that broke it. I guess the thing that would surprise me is, I guess I would just want to know how common it is for Mac users today, because I think a lot of people installed the software at the same time, and it would have installed pretty much all of the same versions I would expect if people are doing it at the same time. And so I would expect Mac issue that they'd all be having the same problem.
Yeah, that's a good question. I have a Mac, but I have not actually tried to do this yet. I can try it and see what happens for me. But what can happen, right, is, and I've had this happen to me before, where I've installed a package and there's been an update to a dependency, and pip will take the newest version of the dependency, even if the people who wrote the software didn't intend for that and haven't added support for the newest version yet. It happened to me with Eleanor. When I was doing it there, I tried to use a newer version on my computer. It downloaded all the stuff, but it downloaded a newer version of a certain package, and then Eleanor didn't work because that package wasn't actually supported. And so I had to downgrade that particular package after installing Eleanor to get it to work. Because pip doesn't always, you know,
coding. The solution I would just love to have is if we could get this to work and then just host it online. So there are several services that come close to offering this level of functionality, but they don't play nicely with the Bokeh widget on the screen right now. So I guess one question I'd have for the Lightkurve developers is why they chose Bokeh for this rather than doing something in Matplotlib, which at least I think is easier to embed on those services that are available.
Matplotlib is a little bit less, a little bit more clunky, I find, with interactive. And so most people, when they want interactive, either go to Bokeh or Plotly, Plotly. And yeah, I've had issues with both Bokeh and Plotly on other things. So one possibility would be if one has a machine that is up and running, you could do a Jupyter Lab or Jupyter Hub, I think. I have not actually tried doing this yet myself.
So there is a website called My Binder, where if you have a notebook on a GitHub repository, you can have My Binder make it executable. So you just have a URL for My Binder, and what it does is it creates a Docker file for your notebook. It installs all of the dependencies, and then all you have to do is access it from any web browser, and there's no issue with cross-platform compatibility because it's all just it's all done in Docker. And if you try a notebook like this, it can do almost everything except for just the Bokeh widget, which ultimately is kind of the centerpiece of this approach, because it's what prevents people from having to really dive into the Python coding. So if there were a web developer who really understood My Binder, that would be a solution. And the other thing too is My Binder is free. So in a perfect world, it could just give all the participants a URL for it, and then they just log in. They don't even have to log in; they just go to that site, and then they can do all this without any local installation.
Can you send me this notebook, Colin? I have one, but it's just a test, and it just has the download. It doesn't have any of the other stuff in it yet.
Sure. Give me a second. I just need to, let me stop the screen share. And I will send that notebook. Bear with me for just one moment, please.
Sure, no problem.
Okay, I've got it ready to go, but I couldn't see who was talking at that moment. Could you just give me your email address, please?
Oh, it's Bert.
Oh, Bert, sorry.
No worries.
No wonder you didn't get it.
Yeah, I got sent one, but it's clearly not the one that you're working from now, because all it has is just the download for the data.
Yeah, the goal of the test was just to make sure that that there weren't going to be any issues with uninstalled dependencies.
Colin, in the Q&A, I put a link to something that might be a way of doing the shareable Bokeh stuff with Binder. I haven't had a chance to go through it all, and I have absolutely no time to do anything with it. But the stuff in there seems to suggest that there is a way around this.
I'm pulling up that link right now. I think I might have already looked at this because I I spent part of a day trying to get it to work, but eventually I just kind of threw up my hands because I realized I was kind of blindly guessing, and there were other last minute preparations I had to make for the workshop. Let's see. Yeah, this is one of the questions that I came across. I think the issue that I was having is that I found examples where people were able to run just plain old Python scripts, but I couldn't find a clear example where there was a bokeh widget embedded in a notebook. So in other words, if it were possible to execute that widget just in the context of a Python script, I could see how it might be doable in my binder, but I didn't understand how to do it from a Jupyter notebook. But like I said, I'm not exactly a web developer by any stretch of the imagination. I'm sure there are people out there who could probably figure out a solution for that.
Colin, this is Ken, and I'm on a Mac, and XZSig worked just fine for me, no problems at all. But I had the same problems with Thuban that everybody else did. In the end, I had to go in and clean up some cached files, and when I tried it again, it worked, but it took a very, very long time to download the data.
So I can think, I think there are several considerations there. If one of the downloads is corrupted, so let's say you start to download the file and then it gets interrupted, I don't know that Lightkurve automatically will clean up the corrupted file. And so if it tries to use the cached version of a corrupted file, you can get issues when you try to run the widget below. But my reaction after downloading Thuban in a different sector on my own computer is that I had similar issues. It just takes forever to download. It's undoubtedly because there are just so many more pixels in that target pixel file.
Yeah, it was kind of a pain to clean up those cache files, but I just stopped everything, closed out the terminal windows, started all over again, deleted the cache files, and then tried running it again and tried being more patient than I was the first 3 times. And after I did that, it worked fine. So not sure what the moral of the story is, but I just thought I'd pass that on if it helps you.
It's a good moral of the story because when I did the example, I had it download it seemed to download in a fraction of a second. And it was just because I was going off of a cached version. And so that would explain why it worked so well for me on the first try, but then not on the second. And then everyone else struggled with it. So I'll just announce that to everyone when we reconvene in 12 minutes, that for everyone else who tried and struggled with it, it wasn't because of something they were doing. It was beyond their power.
Sounds good.
Yeah, they should actually.
Thank you, Ken, for looking into that.
They should add in a little progress bar for the download. I don't know why they don't do that, because then people will know that it's still downloading.
That would be nice if they could add that functionality. And that's
Eleanor does that, so I know it's doable.
That's the sort of thing that like one of the things I kind of like as an outcome of this workshop is maybe just a list of things people would like to see that are different about Lightkurve. And a simple status bar for the downloads would be, I think, a very easy and sensible addition to have, especially for the larger files like that.
Colin, you should go get some lunch.
I'm good to go. I'm running off of adrenaline at this point.
I know, but at least some coffee or something to
Won't argue
keep you
with you
sustained.
there. Are
Colin,
there, oh, go ahead.
No, I was just
I-
gonna say, if you want to take like 10 minutes, which is all you've got left, we have a break video that we can run that has the schedule. It's got a thank you to our sponsors and so on. So we could run that a few times. If you
Yeah,
wanna-
sure. And I'll probably reload on caffeine.
Okay.
Thank you.
Okay, thanks. We'll see you in about 10 minutes.
See you then.
Thanks. Okay.
Elizabeth, I'm not sure who's in charge of everything, but I had a very quick question.
Ask.
Go ahead, Greg. I just had to.
No worries. At one point, I was asking stuff on chat and then chat was disabled.
Right.
If you want to enable chat and just don't want me to be doing stuff much on chat, I'm happy to do so. I didn't
No,
know.
we plan to have chat off during the webinar portion so that Colin wouldn't be, people wouldn't be distracted from what Colin was saying. It wasn't just you, Greg. We just we had it open for people to talk before we started, but it's open right now during the break, but we're gonna close it down again. It's just so that everyone just stays focused on Colin. And since he gave the option for people to ask questions as we go along, it just seemed like it was better to have chat not there.
Oh yeah. No. This is not a criticism at all. The one thing I always find, and this is just my.
Hello?
Oops, you muted me.
Did I? Oh,
Yep.
I'm sorry. I was
No wor-
muting a couple of people who left their mics open from before. Sorry, Greg.
No worries. That's fine. So the one thing I would say is that when we do webinars, I've seen some webinars where you can raise a hand,
Right.
and that might be a way of of easing people into asking the questions.
Well,
As
again,
opposed to
since we discussed amongst ourselves about the raised hand, but since people have the ability to unmute and ask, we'll just let, and Colin doesn't mind being interrupted. We decided that it was just simpler just to do that and not have the other functions there to confuse things.
Okay.
That there's basically one way to do it and not two or three options.
I hear you. I will make one other suggestion then,
Uh-huh.
and feel free to ignore them. Put a statement in the chat when we start again, just reminding people that if they have any questions to just unmute themselves and ask, because every time you log in and log out of Zoom, if I recall properly, you lose what's in the chat.
Okay.
And so I mean, you guys have done that before. Basically, you talked about people can ask questions, but that will be lost for those people that left during the break.
Okay, that's a great suggestion. Thanks, Greg. We'll do that. I'll do
No
that.
problem. Yeah, and thank you guys all for your work. This is just, webinars and webinar management is something we're all getting crash courses in. Like as much as I love the Q&A feature, I also wish there was just a general comment thing that you can put in there, because I sometimes find that there are sometimes things when you're just commenting, which is not, you don't want to distract the flow, but you want to put it somewhere where it will be remembered.
Yes, right. Yeah, it's a different type of a third place for useful information kind of things.
Yeah, but you don't want to. Ideally, they have it all in one thing, so you don't have to go back and forth between.
No, I
three
know.
windows.
I know. You're right.
Oh, I've lived on Zoom before COVID, but now it's even worse.
How many attendees are for this workshop?
At the moment we have 32. We had 37 earlier, and I believe we had 36 people registered. So pretty much everybody has been here who said they were going to come. Hi, Barbara.
Hi.
This is Elizabeth. It's nice to hear your voice.
Thank you.
I'm sorry you were having troubles. It seems like, I guess a lot of people are having issues. So.
Yeah, I just went, I closed everything and started back up, and now everything works fine.
Oh,
like
good.
I have Thuban up, and
oh.
it came up quickly this time. Before it was just stuck on downloading.
It probably finished the download and then it was available. I don't know if you heard the discussion that was going on a few minutes ago with Colin and some other people that someone found that the issue for them was their cache. And by clearing their cache, they got rid of any corrupted versions of the data file that had been trying to download and got interrupted.
Okay.
Clean copy, and then they waited, the download waited, and then there was one clean copy for the program to find, and it worked fine. So
okay, well, now I tried Thuban, and it loaded with no issues at all and pretty fast.
Oh, good. So it must have already
Barbara,
been.
I think that you might be experiencing the same thing I did when it worked right out of the gate for me. And that's simply that I had forgotten that since I had already downloaded that file previously, it was stored in my cache. And so it looked like it downloaded in the blink of an eye when I demonstrated it. And everyone else was downloading it for the first time. And since there's so many pixels in it, it's a very large file. And if someone tried to interrupt that download, which would be understandable because it takes so long, you'd be left with a corrupted file in your cache. And I think that might be the explanation for all this.
Okay.
So that's really just a matter of me choosing a bad example and not thinking through the consequences. So I appreciate your patience with that.
So I can confirm that the shift clip works just fine. And I'm also on a Mac. So it's not a Mac related issue.
Thanks for looking into that, Bert.
No, they are right. When you do reset, it selects all the pixels as opposed to none.
It's one of the acknowledged bugs with it. It's kind of frustrating. I guess.
However, if you do that and then you just click on the screen, it will deselect all pixels and just select one. So it's essentially resetting it that way.
It's one of those quirks that I guess I've grown so accustomed to it over the course of time that it's almost just become background noise. I do kind of wish that the developers would eliminate it though.
Oh, hey.
Barbara, I'm glad to see that you registered for this. I was just glad to see a CV name on the list of attendees.
Oh, nice. I just realized that you can click and zoom, or sorry, you can click and select a bunch of pixels at once by doing a right click and like a zoom in sort of function.
Right.
And then deselect them if you want after that.
I've really been impressed with the tool in spite of its quirks, because when I think of the level of coding that you need to produce something equivalent, it turns into a non-trivial issue. Something even as simple as specifying with a Boolean mask which pixels to extract. It's it's not like it's hard per se, but for someone who's just getting started in Python, it would be like it was in a foreign language.
Excuse me, Colin. This is Elizabeth. Just one quick little housekeeping detail. At excuse me, at 2 o'clock. I mean, 2 o'clock, when our other sponsor is going to present, and Vincent and Andres should have arrived by then. When they log in, I will give them audio and visual, and then you're going to introduce them, right?
Yes, but The only logistical concern I have is that if I get distracted, which based on the past couple hours seems very likely, I might need some kind of cue to let me know that it's time to introduce them.
Would you like a heads up at like 2 minutes of?
Yeah, if you could do that. And I realized that even though I have my phone up next to me and it's on Slack, I've been ignoring most of the notifications.
That's good, because nothing
not,
else has been for you, really.
Yeah, so maybe if you could just make if you'd like to make a direct announcement, it seems like that might be the best way of doing it.
Okay.
I
I think that's the simplest, if I just interrupt you, basically.
Yeah.
If that's okay.
Because otherwise I'll probably just go off on a tangent.
Well, it's hard when people have questions. It's hard to, you can't always stay absolutely to your schedule. Hello? Hello? What happened? Hello?
Colin, I couldn't figure out why your name sounded so familiar, and now I do. It was from the Return of the King paper.
Yes.
I was on that paper.
Which Return of the King? There's been multiple ones.
The FO Aquarius paper.
Yeah, one of Joe Patterson's inventions that he named it the king of the intermediate polars, which has led to just an unending series of puns in paper titles. And I'm the guiltiest person alive of taking advantage of that. Okay, I think most people are getting back right now. Just give me one moment to queue up what I have next.
Okay, and your video is off, by the way, Colin.
I know. I'll
Okay.
switch it back on momentarily, but thank you.
Sure.
Colin, I posted another ring one just for humor.
Sorry, could you say that again, please?
For Colin, I just posted another ring one for humor. Or a king one, Return of the King one.
Sarah, I got your message and I'll let you know. Can people hear me?
Yes.
Okay,
I can hear you.
Okay, great, thank you. The sound changed here for a moment and I wondered if something happened to my sound, but okay, great. Thank you.
I can hear you too. I just had myself muted, but it's
okay. Yeah, I'll let you know, Sarah.
I'm doing a full screen share, so I can't see anything else that's happening.
No, it's a challenge.
Sarah, I'm ready to take over again.
All right, here you go.
Thank you.
Keep on.
Okay, welcome back, everybody. Thank you for sticking around this long. I want to bring you up to speed on a couple of updates during our intermission, as it were. Some of you who are following along probably tried to download Thuban, and there was something I forgot that made it really easy for me and extremely painful for everyone else, it turns out. The reason is that I had previously downloaded the Lightkurve, and it's a very large file because there's so many pixels in it. And because I'd previously downloaded it, my installation of Lightkurve simply used the version I'd already downloaded. All of you were downloading it for the first time, which means that you had to sit through that agonizingly slow download. And that's the reason there was such a difference in the performance between what you saw on my screen and what you experienced on yours. So what we determined is that if you wait long enough and you don't interrupt the download, it will eventually work. And if you interrupted the download, you actually have to go in and delete the corrupted download. So long story short, Thuban was probably not the best idea to have you download, just because it turned out to be more trouble than it's worth. But the larger point of it still stands, that for brighter stars, you can use that technique of halo photometry, where you avoid the saturated core of the stellar image and you just look at its exterior where it's no longer saturated. I want to go over, I think, 2 more targets here. And I want to go through these relatively quickly so that there's still plenty of time to get to the analysis follow-up. So you don't necessarily need to follow along on your own installations here if you don't want to, or maybe you might only do one of them. So I'm going to work through the next 2, ST try. Actually, I'm going to skip over that one. I'm going to jump down to this one right here in this list. Starts out with linear 201 because it has a really excellent example of a well-behaved variable star until all of a sudden there's a huge artifact in the data and it really corrupted it. And I think it's really useful to see what test data can look like when something goes wrong so that you don't start to overinterpret it. So as before, I'm just going to work through the 3 cells in order. Cell A. Click on it. I hit the run button. It asks me for the name or the coordinates of the star. I'm just going to paste in the name from that list. And I got a connection error. If you get an error like this, the best approach is just to rerun the cell. It's probably just an issue with the server or with the internet connection. And this time it executed correctly. Now, a couple of comments about the output here. Don't be alarmed by this message that's highlighted in red. All it's saying is that there were no 2-minute cadence observations for this target, and it summarizes that down here. And when that happens, it means that instead of trying to download non-existent 2-minute cadence data, it's going to instead look for FFI data. So 2-minute cadence is preferred to FFI if it's available. FFI is just the fallback. So we'll be stuck with a 30-minute cadence. And there were 2 particular observations of this particular target, sectors 25 and 26. I've looked at both of these light curves in advance, and sector 26 is the one that's of interest. And you might remember we need to get the number for that observation. In this case, it's going to be 1 from this column right here. So down to cell B, just click on it and run it. It'll ask for that number. I enter in 1. I'm going to go with no quality mask here. And you'll see why, because it really highlights just how awful this artifact is. And with FFI data, we also have to specify the dimensions that we want. So with a 2-minute data, that's predetermined. But with FFI data, you could actually choose pretty much any arbitrary dimension. I recommend about 15 by 15. There's really no firm rule there about that, though. You don't want to go for too many pixels because the file size will be huge. But if you go for too few, you may not be able to get an idea of what the background is doing in each of those images. And that can be one of the dominant sources of error, as you'll see in a moment. So I'll choose 15 in the X direction, 15 in the Y direction. It's downloaded, and now I scroll down to this cell and I run it. And I don't remember the name of the star. It's linear 201. I don't remember the rest. And then I will generate a finder chart for this. And again, just as a reminder, the finder chart software by Ken Miguel at NASA. If you're interested in it, I'll gladly show you how to download it. It's not too difficult, but I didn't want to overburden you for this. Here's our finder chart, and then down here is the light curve and the resulting image. So you can see that this particular target is surprisingly well isolated, and there's a fairly bright star over here, and you can see that for yourself down here. There's the bright star, and there's our target. I'm going to select a few more pixels, but this particular star looks like it's doing something really crazy in here, and it's only an over contact binary, so it should be pretty well behaved, almost to the point of being boring. So let's take a look at what's going on here in the data during these two rises and see if we can figure out what it is. So pay attention to the image over here and see if you can spot anything out of the ordinary. So right now we're still in the good part of the light curve, and now we're entering that rise. And now we're past it again. So now the star is well behaved again. And another rise. This is a classic example of a background artifact, probably just scattered light, maybe from Earth, contaminating the image. So the brightening that we see in the frame, it's not because of something the star itself is doing. It's purely an artifact caused by the background. So when you're looking at test data, this is like one of the best examples I've ever seen of the sort of artifact that you want to rule out. Just see what the background is doing. And in fact, you can even plot a light curve just of background pixels, as I'm doing right now. So there's nothing up there, but I still selected those pixels anyway. And you can see that those pixels are behaving pretty much the same way as the target star was. So this is just further confirmation that that we're seeing a background artifact here.
Can you subtract pixels from other pixels so that you see the difference, the real variation of the star?
So that's a good point. That for those of you who do your own CCD photometry, you're accustomed to measuring the sky background and then subtracting it. And in fact, I did something similar here, and it still had this residual left over. And the reason for that is because you'll note that there's a very strong gradient in this background, that it's much brighter over here at the right side of the frame than it is over here at the left side of the frame. And there are ways that you could deal with this. You can model the sky background not as just a constant value across the entire frame, but rather as a gradient. But then that starts to become difficult to implement. So if you already have Python programming skills, you could implement that kind of solution. Also with Eleanor, there are implementations of background modeling that could handle that, at least in principle. But for the purposes of this notebook, this is one of the most fundamental science limitations of it. The FFI data are not background subtracted. So I had to come up with just an algorithm that would do it without any user intervention, because I don't want people who are unfamiliar with Python to have to try to come up with some kind of background subtraction approach just on their own. If you already have experience, you could consider your own solutions to it. But you're seeing the limit of my approach right here. It presumes a constant sky background. That assumption is violated here. So the solution would be just cut out the bad data, or use a more sophisticated treatment of the sky background.
Is the 2-minute cadence data background subtracted? And is that done adequately in your opinion?
Generally it is. There are some exceptions though. And in fact, with XZ-Sig, you might remember that even if I clicked on pixels that were very far away from the center of the stellar image, you could still see some of those oscillations in the background. So luckily for our purposes, the background was subtracted well enough that the resulting noise is pretty much negligible. But here, it's a whole different ball game. Were there any other questions about this particular example?
Colin, why is that graph is periodic?
That's a good question. So I was looking at this and speculating as to possible causes, and this is purely hypothetical. I haven't investigated it, but I'm wondering, since it looks like it's probably about a 1-day period in there. I'm wondering if it could be caused by variations in the albedo of whatever side of Earth was facing the spacecraft, because I'm assuming that that's reflected light from Earth. And you can imagine that if one hemisphere is mostly covered by clouds and is more reflective, that there might be more scattered light that then reaches the telescope. But again, that's very speculative by me. And if someone knows, knows the answer and I'm wrong, please feel free to let me know.
And you could look maybe for a place which is not too far away from this, yeah, and then it should see the same scattering, right? And if the scattering is very different, then it could hardly come from Earth, right? If you go 5 degrees left or right or so.
It's very likely that it came from Earth, because that is a known issue with Tess, that sometimes its orbit is just going to cause scattered light from Earth to enter the telescope. So it's one of the most common systematics, I would say. So normally you don't see it pronounced quite this badly. This is one of the most extreme background contaminations that I've encountered so far. And in fact, the reason this star came to my attention was that another group had come across it, and they had initially thought that it might be interesting until they realized that the background was doing something crazy like this. So there's one other star that I want to show you, and this one's going to be much more difficult just because it's fainter, but it shows you another type of systematic. Well, not so much a systematic, but rather an artifact that can create a spurious brightening in a star that you're looking at. And this star is going to be V808 Aurigae. So just one single observation, Tess Ffi. For some reason, no one thought to request this at a 2-minute cadence, which is killing me because I probably should have thought of it. It's an interesting star. One more thing while we're waiting for this to load. With the previous star with a horrible sky background, a more aggressive quality requirement, so either hard or hardest, would have killed some of those really bad background measurements. Not all of them, but the Lightkurve wouldn't have looked nearly as horrible as it did. So here's V808 Aurigae. Now, this also gives you kind of a taste of what it's like to look for fainter objects, especially in the FFI data. It's not immediately obvious without looking at that finder chart where the star is, but it's actually right it's about here, and it's heavily blended as well. So this particular star is a cataclysmic variable with about a 2-hour period, and the CV observers who are here today, if you're in the Northern Hemisphere, I highly recommend this star. It's one of the most extreme eclipsing binaries I've ever encountered, where the eclipse depth is like 4 or 5 magnitudes sometimes in the optical, and the eclipse, the ingress and the egress take only seconds to complete. So the 30-minute cadence here is much too slow. But what I want to call your attention to are 3 features. So initially, it looks like there's a a much higher amplitude of variation at the beginning. So here you can see it goes down to about 30 electrons per second and up to 50, whereas a few days later, it's only going from 30 to about 40. And then it jumps a few days later from like 32 to about a little over 50. So that's telling you the mass transfer rate between the two stars. And it's known to vary on timescales of days. But then out here, it looks like there's another spurt where it just brightens a little bit and then fades again. So I'm going to zoom in on that feature. And I'm going to inspect it to see whether it's real. So I'm going to drag the slider over, or alternatively, I could click on one of those observations and pay very close attention to the image over here as I drag the slider back and forth. And I'm going to go frame by frame now so that you can see it a little bit more clearly. Does anyone see what's changing frame to frame?
Yeah, there's a satellite crossing.
Something's going through, yeah.
Satellite or
It's right
asteroid.
here. Yeah, it's a minor planet, and you can see it drifts right through the 4 pixels that we're measuring. And so we know, therefore, that that little bump right there is spurious. It's just caused by a minor planet getting too close to the target. So that's the sort of thing that you should really be looking for when you're trying to determine whether or not a particular feature in your light curve is credible. You should go to that frame by clicking on the relevant point over here, and then you can just move. You can increment the image over here and see if there's something changing between frames that could account for whatever it is you're observing. So any questions about what I've demonstrated so far?
No, just on this one. With a minor planet, you mean a minor planet in the solar system? What kind of planet?
Right, right. So just an asteroid that happened to be in the wrong place at the wrong time. So if one of them passes through the field of view of your telescope, you're just going to see a slowly moving star. And that's what we see here, except it's kind of tough to identify it just because the image is so blurry. It's only when you move it back and forth that you can start to just see it moving through the field of view. So starting here, and then it's going to move towards the upper right. And then now I'm reversing it back to the left. So this is kind of an extreme example. If this were XZ Sig, where it's so bright, you'd never be able to pick out that minor planet there because we're talking about a brightness increase of 5 electrons per second. And with XZ Sig, you're talking about tens of thousands of electrons per second. So the additional contribution of the minor planet would be truly negligible. But for fainter objects, it's always prudent to search for possible issues like that. So any questions about that? Because if not, I will pivot now towards data analysis. Okay, then we'll shift gears and talk about how you would analyze data like this. So there will be kind of I hate to use the term theoretical because I'm not a theorist, I'm an observer, and I'm very proud of it. But I do think it's necessary to give you kind of a non-technical, semi-theoretical overview of like what it is we do during period analysis, because it really facilitates the interpretation of the light curves. And then kind of on a more practical level, the software that we'll be using is VStar. But if you have other period analysis software that you're more comfortable with, like Peronso, or if you already have Python skills and you want to do it all in Python, that would work as well. It's just that I think V star is probably, it probably has the most gentle learning curve of the solutions that we considered. If you'll bear with me for just one moment, I'm going to pull up another document that I prepared. I'm just going to suspend my screen share momentarily while I switch screens. But we're going to be talking about kind of the concept of Fourier analysis. And again, not going into any of the math, not going into any of the really unimportant details for our purposes, but just giving you kind of the bare bones minimum that you should understand. So if you'll just bear with me for a couple of moments while I pull it up. Just out of curiosity, I'm assuming that most people here have not done Fourier analysis previously, although I do know that we have several PhDs here today, which puts the pressure on me to get it right. But if my assumption is incorrect and people already know it, it'd certainly be useful for me to know.
I'm fairly expert at it.
I don't know it.
Certainly used it in the past.
I've used it in the past.
Okay, so
but I have not used VStar. I am very interested in learning how to use VStar.
Well, I tip my cap to the developers because they've, I think they've done an excellent job of designing it.
I've used VStar quite a lot over the last months. It's really a great tool, I think.
Okay, I think I've got this ready to go. My original plan had been to queue all these documents during the intermission, but I'm afraid I got a little bit carried away with other things. All right, I think I'm ready. So I'm going to restart my screen share. And I'll also be grateful if those of you who are already proficient with Fourier analysis, keep in mind, I want to get at this from a very non-technical perspective. But if you think I could be explaining something more clearly, please feel free. It's already happened a couple times today when somebody has offered a suggestion that simplified things. And if you can offer an idea like that, I'd be grateful for it. So let's start with a very basic recap on what a sine wave is, because this is at the very heart of Fourier analysis. So I'm going to just show you this sample here, what a basic sine wave looks like, and two key properties of it: the amplitude, which is basically how high the wave is, and then the period, which is the interval between successive points on the sine wave when it repeats itself. So here, the interval between two successive maxima, just as an example. And what happens with Fourier analysis, and I'm going to use that term very generally here to encompass a wide range of period analysis techniques. So you may have heard of the Lomskargel algorithm previously. Fourier analysis is not, technically it's not the exact same thing as Lomskargel, but the basic principles are close enough, I think, that I'm probably just going to treat them as being very similar to each other, even though behind the scenes the math is a little bit different. The basic idea with period analysis is that we're going to take a light curve with some complex shape, and we're going to try to represent it as the sum of a number of sine waves like this. The difference, though, is that the sine waves will have different amplitudes and periods. So let me give you kind of a concrete example of what this might look like with a simulation that I put together. So in this upper panel, I created this black line, which is a simulated light curve of an eclipsing binary. And this green curve right here is what you get if you try to fit a sine wave, just one single sine wave to represent that light curve up there. And you can see it doesn't really do a very good job. So on one hand, the minima of the sine wave do match up with the minima of these simulated eclipses here, but the fit is very poor. The green line, the sine wave deviates from the simulated light curve on most points. But the key idea with Fourier analysis is that you can keep adding more and more sine waves together. So rather than just one, you could maybe increase it to 2 sine waves, for example, and you'll get a slightly better fit. And so I'm going to drag a slider down here to demonstrate this. So this green curve now is the sum of 2 sine waves that represent that light curve instead of 1. And I'll just flip back to the single sine wave fit. You can see it looks a little bit better, but it's still kind of a lousy fit. So what if I add a 3rd sine wave and a 4th and a 5th and a 6th? You can see that as I add more and more of them together, I'm increasingly getting a good representation of what that light curve looks like. So just by adding those 6 sine waves together, I'm starting to get a respectable looking model of the observed variation. And the idea here is that if you could add together an infinite number of sine waves, eventually you could represent any observed light curve. So if I kept adding sine waves here, that green curve would eventually have an excellent fit with respect to the simulated light curve. Which brings us to the power spectrum, which I suspect many of you have seen before, although I don't know how many of you have had to work with it directly. I know some of the amateur astronomers have published really impressive papers based on power spectra. So this will, for some of you, this will seem rudimentary. Others, I know it's going to seem kind of intimidating. So I don't want you to get bogged down with the details here. Just try to stay focused on the astronomical applications of this. So the power spectrum is the term that we give to this figure right here. The x-axis refers to the frequency, which I've used the term period, but I haven't defined what frequency is yet. So you're all familiar, I assume, with the concept of a period of a light curve. For example, an eclipsing binary with a period of 2 days. It means that the orbit will be completed in 2 days. The frequency is the reciprocal of the period. So in the example of a 2-day period, the reciprocal would be 1/2, which is 0.5. And the units for that are cycles per day, which is kind of weird when you're accustomed to working in periods. But it just means that each day, half of an orbit will complete. I think that's the most intuitive way of thinking about it. And power spectra are normally visualized in terms of frequency on the x-axis. And on the y-axis is a statistic called power. Sometimes you'll see it plotted just as the amplitude of the sine wave, but essentially the value of the y-axis is indicating how well a sine wave at a given frequency represents the light curve. So let me clarify that with this example here. If you look at this peak here, about 47 cycles per day, you can see it's well above the surroundings over here down in the noise. And that means that a sine wave with a frequency of 47 cycles per day does a reasonably good job of fitting some of the data in the light curve. And same thing over here for this signal at about 24 cycles per day. The kind of the flip side of that would be if you look over here at, I'm just picking a random spot on the x-axis, 35 cycles per day, where I'm hovering the cursor right now. You don't see a significant peak there. And that's saying that there's really not much sinusoidal, there's not much of a sinusoidal component at that particular frequency. And so the way to interpret this particular power spectrum is that if you took a sine wave with a frequency that matches each of these peaks, and you added all of those together, you would be able to represent whatever signal you're studying. So in this example, the signal that we're studying is this simulated eclipse light curve up here, the black line. Now, I'm not going to lie, if I were encountering that for the first time, I would be scared. And in fact, I was scared when I encountered it for the first time in class. It's never going to seem terribly intuitive the first time you encounter it, especially when I'm the one doing the explaining. It's only going to muddy things, I fear. I'd say that it falls under the category of you don't necessarily need to have a fundamental intuitive understanding of what a power spectrum is when you get started. If you start out just with kind of this broad framework that it's going to show you how sinusoidal a signal is at a particular frequency, and you go from there, I think that that's enough that you need to get started. And then the more work you do with it, the more intuition you'll develop for it. So this, perhaps a simpler way of conceptualizing this power spectrum is that it's showing us that that most of that light curve can just be represented with 1, 2, 3, 4, 5, 6, 7, 8 sinusoids added together. And this is essentially what's happening when we do a power spectrum, which is what we'll use V-star to accomplish, that we're going to try to represent the light curves that we extract from Tess as the sum of a bunch of sine waves. And we're going to use that to identify what periods are present in the data. The reason I'm kind of going into more of this conceptual framework rather than just telling you to calculate power spectra is because it's easy, I think, sometimes to misinterpret power spectra if you just think of it as a magical technique that somehow is able to identify a period in a light curve. Because one of the traps people will fall into is they'll just look for wherever there's the light curve, and they'll say, oh, that's what the period is. And there are some subtleties to it that we will encounter later that really force you to stop and think kind of conceptually about what the power spectrum is showing you. So just to give you an example, those of you who study over contact binaries, you know that there are 2 maxima per cycle, per orbital cycle, and 2 very nearly equal eclipses. And so if you take a power spectrum of one of those stars, you're going to see a very strong peak at what looks like it's a plausible orbital frequency, but in fact, it's incorrect because it's simply because the light curve, the period will actually be twice what seems to be indicated in the power spectrum. And it's because all the power spectrum is telling you is how sinusoidal the light curve looks at a particular frequency, not what the true frequency necessarily is. So it's kind of might seem like a subtle distinction, and that's why I want to get to some light curves so you can actually start to see this in practice. So again, if this is intimidating, you're not alone. I found it scary too when I first encountered it, and eventually I just got used to it. And I think this is where most people think that it's most difficult when you're analyzing light curves. So don't let this intimidate you. You're in good company if you find this difficult looking. So I'd like to take questions or comments now. And those of you who are already proficient in Fourier analysis, and or Lam Scargle, please just jump in if you have any insights that might clarify this.
Yeah, this is Greg Donahue. Can you hear me?
I can.
Hi, Colin. So in the harmonics down below the number, is it, as you increase that, is it just picking the peaks there, the first one, the second, third, as you go down from the power spectrum?
Correct. Yeah, so this number over here where I'm hovering my cursor, that's telling you the number of sine waves that are being added together. I can keep adding that and the fit gets better and better, or I can decrease it all the way back down to 1 again. And there's our single sine wave fit. It matches the period, but doesn't actually fit the Lightkurve very well.
But it's picking the actual sine curves that we see that are in that power spectrum. If you pick one, it'll be that first one.
Correct.
Okay.
And I'll just pose a kind of a quick conceptual point here. I've given you kind of a simulation of an eclipsing binary, but imagine you were looking at a purely sinusoidal Lightkurve. So imagine if that that thick black curve there, imagine it were just a perfect sinusoid. The power spectrum would look very different then, because if it's just a sine wave, this may seem very trivial to point out, but you can represent it as a sine wave because it is one. You can represent it perfectly, in fact, as itself. So in that case, the power spectrum will show just one peak at the frequency of the Lightkurve, because it's just a way of saying that a sine wave can be represented as a sine wave. The reason we see all these additional peaks here called harmonics is because we have to add those additional sine terms to start to do a better job of representing the non-sinusoidal shape of the Lightkurve.
There's another thing that is an interesting thing. There was sort of the relationship between the two, the Lightkurves and the power spectrum. And that's generally, if you look at power spectrum, things that are very thin in the power spectrum, like these peaks at 25, 48, etc., those tend to be corresponding to things that are very wide in the Lightkurve. And things that are very short in the Lightkurve tend to be signal aspects that are seen in the more wide stuff in the power spectra. So there's a relationship there that can be very useful as well.
In fact, you're reading my mind because I have another demonstration that will show that. In fact, that'll be the next thing I pull up, but that's an excellent point. Are there any other questions or comments about this before I move on? Okay, so this should only take, I'm hoping, a couple of moments to do, and then we can turn our attention to V star. So let me get this so that they won't overlap like that. Oops. I just don't want the labels to be overlapping. So here in the top panel, I have a simulated Lightkurve that's perfectly sinusoidal. And in the bottom panel, I'm showing the power spectrum of it. So here, as I said, if the Lightkurve is a perfect sine wave, you see just that single peak there. But let me show you the effect of the duration of the power spectrum, or excuse me, the duration of the Lightkurve. So up here, this is a period of about a day, and the length of the Lightkurve is about the same. That peak is very wide and it's ill-defined. And then as the Lightkurve gets longer and longer, you'll notice that that peak there is getting narrower and narrower. So if this Lightkurve were infinitely long, you would just have an infinitely narrow peak there at the frequency of the Lightkurve. In terms of like what this actually means for astronomy, and as opposed to just some mathematical curiosity, the width of that peak tells you the precision with which you can measure the period. So over here where that peak is extremely broad, you can't really measure the period to a high level of precision, whereas in this situation where the light curve is 28 days long, similar to a Tess observation, that peak is much more narrow. And so you can measure the period much more precisely in that case. So this is just another argument for why you want these Tess light curves when you're measuring periods, as opposed to just, you observe it once with a ground-based telescope for a few hours and then move on. There's much greater precision in this case.
Colin, do you have a sense for what the minimum number of periods is a good idea for people to consider before they think something is periodic? This is one of the tricky questions in doing periods. So I'm not trying to lay a trap for you.
No. That's a very logical. It's inevitable that you come across that. I'm planning to get to that once we jump into V-star and we see the appropriate, we see the corresponding dialog boxes in V-star where you have to fill in that information. And then I've got another resource that we can turn to there because there are some rules of thumb. So for those of you who may have missed that question, the idea is that in order to calculate that power spectrum in the bottom panel, we have to tell the software which frequencies it should be checking for periods, because it's not that you just say, here's a light curve, tell me what periods are present in it. Generally, if you want good results, you're going to have to explicitly tell the software which frequencies it should check to see if there's a sinusoidal component at that frequency. And so that's a big part of the process. And we'll probably get to it in about, probably not before the message from our sponsors, which will be at about 2 o'clock. But we will get to it shortly thereafter because it's one of the big points today. And I do want to try to make sure that we leave enough time at the end so that you can try some of the light curves I've selected for eclipsing binaries and short period pulsators. So any other questions or comments about this? In that case, why don't we go to V-star? So if you already have it on your machines, I'd ask you to start it up right now, which I'll do on mine. So in order to load the light curve observations, first thing you need to do if you haven't done it previously, and I expect this will be for most people because I haven't previously asked you to do this because I think it's very straightforward if you already have V-star running. Go to the tool menu, select plugin manager. And the plugin that we will need is Lightkurve Output Observation Source V0.2. Now, in my earlier tests, I also needed to download this one, Kepler Tess Fits File V2.2 Observation Source. But I think that bug was taken care of so that you only need this one. But if you get error messages, the solution will be just to download both of them. So it's not giving me the option to install here just because I've already installed it. But once you install it, it's probably going to ask you to restart V-star. That's normal. Just go ahead and do it. And once you've restarted V-star, go to the File menu, hit New Star from File. And on desktop, I think I've got a FITS file in there. If not, I'll have to just go back and create a new one. The only tricky part here in the open dialog box is you have to go over here to source where it says download or simple. And you want to choose Lightkurve fits v0.2. And sure enough, it looks like I forgot to save a file there. So let me just copy one over. Or in fact, I'll just navigate to a folder on my computer where I know that there is one.
Colin,
Yes?
could I just point out that there's another way possible to open the file if after you've installed the Lightkurve plugin and restarted VStar, at the very top of your VStar screen where it says File, Edit, View, Analysis Tool, Help, if you click File, you should see Open with Lightkurve plugin.
I saw that in a previous version of VStar that I tried,
Yeah.
but the only way I've seen it in this version is to
Do it this way. Okay.
Yeah.
It worked for me actually, but I don't know, maybe not for
Are you using version 2.21.2?
That's right. Yep. But anyway, if the other way works, that's fine too.
Yeah, I'm kind of at a loss for that.
Can you quickly say again which module, which plugin to add? What was the
Certainly.
name?
So
Yeah.
Tool Menu Plugin Manager.
Yeah, sure. And then?
And when it pops up, Lightkurve Output Observation Source v0.2. You might have to scroll down a little bit because I believe that it shows the installed plugins first. And I have those 3 already on my machine. So you probably have to go down a little bit in that list to find it.
I don't have that one. And if I open my VStar, I see 25 plugins which I all have in, but I do not, I have the Kepler test fits file, v2.2 observation source, but I do not have a Lightkurve. Is this a standard plugin in VStar?
I don't have it either.
Okay.
Right.
I'm not alone. Thanks. Feels better.
It was just uploaded to that plugin manager last week. But I'm
okay.
still surprised that it does not show up for you.
Is there anyone who does see it in their plugin manager?
Yes, I see it in mine. I just
What
installed it.
version are you running?
Is that in the help, I guess?
No, it's on the up, just in the header line at the very top. VStar, and then there's a number.
2.21.2.
Yeah, I think it's not a version, but maybe the time of installation matters, right?
Oh, I have one other suggestion. On the toolbar of VStar, where that pink gear is in the icon, if you click that, there's a tab that says plugins, and I believe it says where the plugins are coming from. That, yeah, exactly like Colin has. That's what you should see: plugin location, base URL, and that shows it's coming from our server where that plugin is located. And then you can click this button here below that says show all observation source plugins in file menu. Maybe that's why you didn't see it, Colin.
Ah, yes, I
And
think
then
that's
apply, and then okay.
Before I leave the screen, has everyone else who has not been able to locate the plugin, have you been able to get to this screen to the plugins and then see the plugin location, the base URL?
Not yet. The plugins. Yeah. Okay.
I'm there, Colin, but mine says 2.20.0.
And my says .1.
Okay, make it 2. If you make it 2, I think you'll find the plugin.
Oh. Select local directory then, or?
Sarah, my understanding was,
yeah, go ahead.
With people using the .jnlp launcher, so what they get when they just go to aavso.org/vstar, that should automatically give them the most recent version, should it not?
Yes, it should.
It
But-
did not, Sarah.
Well, anyway, fix that URL for the plugin location to make it look like Colin's. Click the button below that says show all observation source plugins in the file menu. Click apply and then click OK. And then you'll probably have to, well, I don't know if you have to restart VStar again before you go to the plugin manager or not, but.
Does anyone still need to see this URL here? Okay.
So,
Go
Matthias,
Yeah.
I did what Sarah said because I was having the same problem. You don't have to restart before you type in the .2. Just hit apply and OK, and then
I have it now. Yeah. Lightkurve
Yeah.
output observation,
Good.
right?
Yeah.
Okay, good. Great. Thanks.
Yeah, Sarah, I'm glad you you thought of that.
I ran into it myself a couple days ago.
You saved the day.
Sorry, I missed which plugin we're loading in all the.
Sure. I'll just pull it up for you so you can read it off the screen. So tool plugin manager, and it's Lightkurve output observation source v0.2. And it's going to be buried down in the menu because
I believe they're in alphabetical order. So if you didn't already have it like Colin does, you see it under the Kepler one. Scroll down.
Got it. Thank you so much. I apologize. I missed a key second.
No, not at all.
And then hit install and then restart VStar.
And then I was, for those of you who missed it, if it doesn't create a new entry in your file menu, just go to New Star from File, Source, make sure you select Lightkurve Fits.
It creates a new entry. Yeah, that's great. Yeah. New stuff from Lightkurve. Yeah, it should be there.
And I'm also, I should add that I'm assuming that perhaps without cause that you've all saved a FITS file from one of the previous examples. So if you haven't, you can just go back, maybe like XZSig. I wouldn't recommend Thuban because we know that that particular data set is cursed. But XZSig or ST-try or something that will download quickly. And then when you create the Lightkurve at the bottom after cell C, there's a green button that says Save Lightkurve. You just click that, and that will save your Lightkurve in this FITS format, which you can then load into VStar.
Sorry, Colin, I've uploaded the Thuban FITS file to the question and answer dialog box.
Sorry, could you say that again, please?
Yeah, you may find the Thuban FITS file on the question and answer dialog box in the window. It's a Dropbox link.
Get that. I'm going to pause my screen share momentarily.
Colin, I'm sorry to interrupt. This is Elizabeth. I'm sorry to interrupt you, but it's 2 minutes. Your 2-minute warning.
Okay.
Thank
Okay,
you.
let me just follow up on that question. Carlos, I think was it you who asked that question, or you pointed that out, right?
Yeah, just
so your point in the Q&A was that Thuban is this star, and then you gave its catalog number in the Tess input catalog. Both designations are recognized when you query the source by its common name. So it recognizes Thuban, but it also can retrieve it as TIC 165991532. So it'll still lead you to the same data source. We determined that the problem there was that the Thuban data file was just humongous, and it took too long to download, and sometimes the download was being interrupted, which left a corrupted FITS file that couldn't be loaded. And so the solution was you had to go into the cache and delete that file. Perhaps the easier solution was I should just have not chosen that particular star. But I do appreciate you following up on that. Elizabeth, I think this would be a logical point to have our sponsors. And so they're from OBSTech, Vincent Suk and Andres Jordan. So if they're ready to go, I'll happily yield the floor to them.
Thank you, Colin. We're just giving them permission.
Okay.
Sarah, could you please give Vincent and Andres permission to speak and use their video? They're panelists. You're muted, Sarah, if you're trying to say something. Sarah, okay, great. You're doing it. It's happening. She's getting it. Great. Thank you, Sarah. Vincent and Andres, you should be good to go. And welcome.
Thank you. So we're delighted to be sponsoring this event. I'm Andres Jordan. I'm a professor of astrophysics here in Chile. Vincent is an optical engineer. We're both working at Universidad Adolfo Ibáñez in Santiago. And back in 2013, we started on a quest to fulfill a dream we had, which was to fund an observatory in Chile that would allow many people to enjoy the skies of Chile, the same skies that were being enjoyed by the professional international observatories in our country. And we found a mountaintop. We fitted it with a high-speed internet, power, and all that it's required to observe remotely. And right now we have close to 50 telescopes, all the way from setups for astrophotography, science project, same level that the ones that are going to some professional observatories, and also groups doing space situational awareness studies. We are at the moment 8 people, and yeah, we're going to show you a 5-minute video presenting our observatory, and then we're going to take any questions that you guys might have.
I'm sharing the video. Wait a minute. I'm Vincent, so I'm CEO at OBSTech. I'm in charge of the organization and what's happening at the observatory. So OBSTech started in 2012. We started as investigators of the university, and we had telescope in Las Campanas. And the idea was to make an alternative to amateur astronomers and professionals for having a site for robotic telescope. The observatory at South started at very little, a single building at the beginning with only 2 amateur astronomers, 2 small telescopes. And now it grew up to 37 telescopes actually running on site, 40 by next month. And we are building a new building for 11 telescope, which is almost full. And they will start another building for 11 more telescope. The idea of OBSTech for the next few years is really push on one side on amateur astronomers for having the best service for amateur astronomers in astrophotography and collaborative science. And this real high-end alternative will give the best service for amateur astronomers.
Samuel Robert. I am the CDO of Obstec, mostly concerned about the development of new technologies in the observatory, and also I take care about the systems that make possible this observatory to work remotely. The main specs of this observatory are a very high bandwidth of internet. We have 3 independent connections. One is a 100 megabyte symmetric fiber link, which is the same one that is gonna feed the new LSST project in Cerro Bachon. Also has a second radar link, which is about 70 megabyte symmetric bandwidth. Observatory is powered by a solar plant. So we have more than 20 kilowatts in solar panels generation. This site is a world-class observatory. In terms of clear nights a year, we have in average more than 300 clear nights. Last year, 2018, we had 320 clear nights a year. The average seeing is around 1 arc second, mostly below it, depending on the season of the year. And we have normally low humidity. There's no much wind during the night, so it's a very good site for a telescope to up 1 meter.
Hi, I'm Jonathan. I live on the site. I'm here to keep an eye on your setup, to collimate, to installing or cleaning your equipment, to be sure all is fine.
Hi, I'm Rodrigo. I am an automation engineer. I take care of hardware development of the observatory. I work in Santiago, but periodically I go to the observatory to perform the upgrades and maintenance in the observatory system. This is my job.
Hi, I'm Abner. I'm finishing my PhD in astronomical instrumentation and recently joined to Obstec team as manager operation to oversee all the support and administration. I'm in charge of manage the people that works with us. That includes technician support and the guards.
The observatory is not only growing in terms of number of telescopes and buildings, but we are also growing in terms of activity. We are doing a new workshop, new dorms for people working on site. And here behind me, we are building a new house, mostly for amateur astronomers who want to come here to stay on site, either to install their equipment or just for stargazing and having a large Dobsonian telescope to take the best advantage, the best site in the world for stargazing and real visual observations. Thanks for listening. So we can take a few questions if you want to explain a bit what we are doing and any doubt we may have regarding what is our activity here.
Vincent, I have a question.
Yes.
What you just showed us is a dream for us, I would say. So very, very interesting. Thank you. Can you perhaps elaborate a little bit more with respect to the costings involved? I know that you have a rate, an annual rate that one has to pay for the maintenance, but what about the equipment? Can you take care of getting the equipment, or is it up to the owners to bring it up there, make sure that all the components are there, and then you can take care of the maintenance of it? How does it work?
So what we usually do is we typically help the owner along all the process. I mean, we can give him some tips for sending all the equipment and all these things. They can directly ship directly from the constructor if it's new equipment, or shipped from their own site if it's a second hand. In any case, we can give you the good context for shippers and to get it into Chile. And then when the system arrives in Chile, we have contact with our own custom agent, and we usually deal all things with them. So we estimate before the system arrives how much it will cost in terms of customs, VAT that we have to pay here, and all the associated cost of the agent, these kind of things, shipping inside the country if necessary, and these kind of things. And we estimate it beforehand, before you send it, so we can change it in advance, and so that we can handle all the process in the meantime. Then from the moment that the system arrives in Santiago, depending on the size, we can either load it in our pickup to drive it up to the site. For very large instruments like 24-inch and more, where we would need a truck, we take care of reserving the truck, putting it into the truck, having a crane ready for when the system arrives. Then we can handle the installation if you want. You can come if it's non-COVID times to install yourself as you are also. We can receive you on site if you want to be there, or we can perform all the installation ourselves. And then usually for the installation, we charge, if we do the installation, we charge an extra of, it's around $2,000, depending on the size a bit of the telescope, but not much more than that in any case. And then all the service during the hosting is all included. So our hosting service for people who will register before the end of the year will maintain the 2020 prices, which is in Chilean pesos, it's 6.5 million, which is roughly $8,400 US dollars per year. And this includes everything that we could do over the year. I mean, it's telescope handling, periodic cleaning with CO2. If there's any problem, it includes the service of checking what's happening. Obviously, if we have to change parts, I mean, you would be in charge of sending new parts or the kind of things, but it includes all the service you may need on site. So we really push on having the really best service on site, to have really the people happy of what they are doing, to take advantage of the biggest number of nights over the year. I mean, our site, we have more than 3,300 clear nights a year. And we really want to take advantage of that for all our customers. So this is a bit the idea. I mean, obviously, I mean, we are not shippers, but we really want to help people all over the process so that they wouldn't have to bother or be worried about if the system is shipping well.
Yeah, just to, yeah, once the equipment gets in Chile, we take charge of everything so that it gets to the mountain, as Vincent said, either on our own pickup or in a rental truck.
Thank you very much.
Andres and Vincent, thank you so very much for your presentation. I think our time slot is finished for this. Maybe if people have more questions for you, they can email you and hear more about this incredible resource that you're offering to all of us.
Yeah, most certainly. Don't hesitate to write. The email is there, info@obstec.net. And yeah, thank you.
Thank you very much. And again, thank you so much for the sponsorship of this workshop. We're extremely grateful to you.
Thanks to you.
It's a pleasure.
You're welcome to enjoy what's left of the workshop if you'd like. Thank you again. Colin, it's back to you.
Thank you. And thank you to both Vincent and Andres for that talk. I'd like to, in the remaining time that we have, we'll do some V-star, because I still need to show you how to do power spectra in V-star, and some of the practical considerations of it. But I do want to make sure that we still have time at the end for our breakout sessions. In particular, there are a couple of stars, especially with the eclipsing binaries, that where we can have some immediate, tangible science benefits from the test data. But without further ado, I'll resume my screen share and I will jump back to where we left off in VStar. So for those of you who have saved a Lightkurve and have loaded it, you should see something like this. And again, I'm assuming that earlier on, when we were creating Lightkurves in Python, that you hit the green button that says Save Lightkurve. I think in all of my excitement that I might have forgotten to actually explicitly say that you should click the button that says Save Lightkurve, even though it was, in fact, an important part of the process. So when you load a Lightkurve of, for example, XZSig into VStar, you'll see something like this. And those of you who are accustomed to observing RR Lyrae stars just with your own telescopes, I think you'll agree that this is significantly better sampling than what most ground-based observers are accustomed to having. Just this wonderful, uninterrupted, continuous observation. A quick point about the y-axis here. VStar defaults to magnitudes, even though Tess is usually expressed as just a flux. So in other words, a count rate, the number of electrons per second at a given pixel. This particular magnitude is completely arbitrary. It's what we refer to as an instrumental magnitude. So you just apply the mathematical definition of what a magnitude is to it, but it's not on a standard scale or anything. So the fact that you see magnitudes from 3.4 to 4.2, don't read anything into it. To do
Colin?
Oh, go ahead.
Does that mean that the VStar is incorrectly counting these as taking the flux data and just assuming that was a magnitude, or does VStar at least also do the logarithm, the minus 2.5 log correction?
No, that's exactly what it does. It just for the flux, it takes the number of counts, and then it applies the definition that you just mentioned, negative 2.5 times log base 10 of the flux, and then it might add a constant as well. But the bottom line is it converts it to an instrumental magnitude, and then it also applies a correction to the error bars, which were originally calculated as flux. It converts them to magnitude uncertainties. I think that if there were enough demand to analyze Kepler and Tess in VStar, that could potentially be the sort of feature that we might request in the future, that it handles flux natively as opposed to converting to magnitudes. But you can still get substantially the same results just by working with magnitudes. It's just that I think flux is a little bit more intuitive once you get used to it.
Just as information, I just loaded in VStar the AAVSO data for the Johnson V band, and that, which of course is another band, right? So, but it is between 8.7 and 10.2, maximum and minimum. So that is what you normally would get if you look into the light curves of the V bands.
Thank you for looking at that. It's useful to know, because one of the other things you'll notice about this Lightkurve is that the amplitude that you see peak to peak is significantly less than what you would see in bluer bands. It's just a property of this type of star, that the pulsation amplitude is expected to be lower as you get to longer wavelengths. So why don't we do a period analysis of this? So this is going to be, I think, kind of a, I think this will be comparatively straightforward in relation to some of the other examples you might come across, because I don't to my knowledge, XZ-sig isn't one of the more extreme examples of a period of a pulsator that's changing period. Though if somebody knows to the contrary, please correct me. But that means we can compare the period we get against the one that's in VSX, and we can see whether they agree. And I don't want to spoil anything for later on, particularly people in the who will be going to the Eclipsing binary breakout session. But I can tell you that one of the stars I've chosen for that, you'll find a period that strongly disagrees with what's in VSX. So to do a period analysis in V-star, you have a couple of choices. I suggest going for one of these. So DC DFT, which I believe is date compensated discrete Fourier transform. And I would suggest going with the middle option here. So with frequency range. If you wanted to, you could also do with period range, but I think it's best when you're working with power spectra just to make the mental transition to working in frequencies, because it's just more natural and it'll save you trouble in the long run, even if right now you're accustomed to working with periods. So I selected the data, the Lightkurve, okay. And this box right here was the subject of a question I received about half an hour ago. And this is where you actually specify what frequencies you want V-star to examine for your power spectrum. And I think this is probably the most crucial part of the analysis, because you need to make sure that you specify a range of frequencies. So starting from the low frequency to the high frequency, you want to make sure that you're encompassing a range in which you expect the star to be variable. And you also need to select a resolution parameter. And that part, I've got an illustration to help you understand it, because just seeing it right now, it doesn't really, I don't think there's much intuition for it. Keep in mind, we're working in frequencies here. So for this particular star, XZ-sig, I don't remember the exact period. I think it's something like 13 hours. So I'll round it to half a day. If you convert half a day into a frequency, you get 2 cycles per day. So I'm going to select a wide frequency range here just to make sure I get the frequencies that are in the data. So I'm going to start with the low frequency of 1, and we'll revisit that later because we can actually be a little bit more aggressive than that. And I said that that we expect the period to be about half a day, so 2 cycles per day. I'll go all the way up to 10 to make sure we get it. In practice, we can actually go much, much higher than that. But I'll show you that in a subsequent power spectrum. And then the resolution is the step size. So in other words, when you specify a low frequency of 1 and a high frequency of 10, it's going to start by examining a frequency of 1 cycle per day. It's going to see how well a sine wave fits the data at that frequency. And then it's going to increment according to the resolution. So for example, if I were to specify, and I don't recommend this, a resolution of 0.1, it would then repeat the procedure except at a frequency of 1.1 and then 1.2 and so forth until it gets to 10. It's a good idea to specify a fairly small resolution there, a small value of it, to ensure that your step size is small enough that you don't overlook a frequency. Because if you choose too large a resolution, so for example, maybe 2, it would just, when it's performing this analysis, it would completely miss genuine frequencies that are present in the Lightkurve. And in a moment, I'll show you a graphic that I've prepared that kind of illustrates this, so that you might develop more of an intuition for it. Because I think just hearing it in words isn't always the best way of presenting. So I will try 0.01 just for starters, and we'll see what that looks like. We can revisit these parameters later. So again, this is going from 1 cycle per day to 10 cycles per day. And we're expecting that we'll see a frequency at around 2 cycles per day. So let's see what this looks like. And I will maximize that so you can see it a little bit better. And sure enough, we do see a frequency here. And there's a table that I can show you on another tab that will give us a more precise measurement of that. But I do want to call your attention to the appearance of this plot right here. So this power spectrum looks kind of jagged. You can see that there are discrete line segments like here and here and here. Whereas previously, with those simulated power spectra I showed you, they were much smoother than that, that they looked like very smooth curves rather than jagged lines. And I'll show you, I keep promising you that illustration, and I think it's going to make more sense when you see that. But if you see the summary of this is that if you see a power spectrum that looks jagged like that, where you can actually see line segments instead of a smooth curve, it means that your resolution is too coarse. You need to choose a smaller value for that. Now, VSTAR makes it easy to figure out what that frequency is because it generates a table that summarizes the main signals that might be present in that power spectrum. So you'll see here, it detected something at a frequency of 2.14 cycles per day. It converts that to a period, so just 1 divided by 2.4 equals that number. And then it gives the power, which is the Y value, and then the semi-amplitude. So what is the semi-amplitude of the corresponding sine wave in magnitudes?
Colin, since you
Yes.
talked about the sort of this jagged versus a fine power spectrum, you want to comment about the difference between trying to, like here we know what the frequency, what the period is, but the sort of the difference between doing a rough thing to try to figure out where you might have to go in and actually doing the refinement, why you want to start rough and go in fine?
Absolutely. So power spectra can be computationally intensive because you're potentially asking the software to examine millions of frequencies in some cases to see whether or not there's a significant sinusoidal signal at that frequency. And when you start doing that for millions of frequencies, it can really slow things down. And there's benefit to doing kind of this initial rough guess rather than searching millions of frequencies. You do just, in this case, you know what the approximate frequency should be. So you do kind of this initial guess that's not very precise, but it gives you information so that you can do a more targeted fit. So for example, this peak that I have on screen right now, you can see very clearly that it's around 2.15 cycles per day. And what I'm going to do in the next screen is I'm just going to go from 2 to 2.3, and I'm going to do it with extremely high resolution and just make a mental picture of what that jagged line looks like. And in fact, I'll save it so that we have a point of reference for it.
So while Colin's doing that, I'll also comment that when you're looking for a new period, the more frequencies you look at, it's like looking under a lot of rocks. And if you look under enough rocks, you're eventually going to find that really rare object, but you don't know if that's an object that you're actually looking for. So there's a penalty in discovery space if you look at 1 million things and find one odd thing, versus if you look at 100 things and find one odd thing. You're much more likely that that one odd thing, when you only looked at a few things, is actually real and not just some statistical fluke. So it's always good to start with these rough ones first when you're doing a discovery space as well. And
thank you for making that point. In a few minutes, I'll also give you kind of rules of thumb that you can use with test data, because there's some benefits just because of the sampling that you normally wouldn't have with ground-based observations. Kind of gives you an idea of what frequencies you can meaningfully study. But for now, I just want to follow up on an example of a high resolution power spectrum that's just targeted at that very narrow frequency range around that jagged peak that we saw a moment ago. And so I'm going to run this. And notice it's taking longer. Even though I was searching a narrower range in frequencies, I was doing it with a much smaller increment. And now you'll see that that power spectrum, rather than looking jagged, all of a sudden it's looking much smoother here. And in particular, we've done a much better job of measuring this peak up here. And I'm going to use this as a segue to that graphic that I mentioned to you. So this is from a document that I'm going to circulate to everybody that kind of summarizes this. So I don't want you to feel like you have to be memorizing this the first time you hear it. What I did here, these three panels, the top one is a power spectrum of a simulated data set with extremely coarse resolution, kind of like that first example that I showed you with V-star, except even more extreme. You really don't see any peaks in there. This middle panel is a power spectrum of the exact same data set, except it's with extremely high resolution. And they look nothing alike, those two panels, so 10A and 10B, even though, again, it's the exact same data set being analyzed here. And the bottom panel shows you what the difference is. So these red dots here are from the high resolution power spectrum, that middle panel, with the extremely fine resolution. The black points are from the top panel with extremely coarse resolution. And what you'll see is that the peak that we were looking for, it actually fell between the frequencies that we were studying with the low resolution power spectrum. The high resolution power spectrum, on the other hand, does measure it. The analogy that I like to give to students is that if you're measuring the elevation profile of a country, so use the United States as an example, if you just measure it on the beach on the East Coast and the beach on the West Coast, and maybe in the prairies in the middle of the country, it's going to look very flat if those are your three data points. But if you measure it much more finely than that, every mile as you go coast from coast, you're going to be able to measure a number of mountain ranges in between. And it's not because the elevation profile has changed for some reason. It's just because you're doing a better job of measuring what you're trying to measure. And it's the exact same concept with power spectra. And so this is why for your final analysis, you do want to err on the side of high resolution when you're trying to get a really precise measurement of a peak in the power spectrum. Does that make sense to everybody?
Yes.
Okay, I don't hear any objections, so I'm taking that as a positive sign. I think I'm going to have to rush things a little bit because I do want to leave time for breakout sessions. So one final point I want to make about power spectra is kind of the range of frequencies that you can meaningfully probe. So in the example I did in V-star, I was trying to just search for the main frequency that I knew ahead of time would be present in the Lightkurve, because VSX was pretty accurate with the catalog period of it. So I already had a pretty good guess of where I should be looking. But let's say you want to search all meaningful frequencies in the test data. That brings us to a discussion I have here. And again, I don't expect you to know all this right away. Just make a mental note that it's there in this document that I've prepared if you want to return to this issue later on. I have a rule of thumb for the low frequency that you search for. So for a 28-day Lightkurve from Tess, my rule of thumb is that I want to see at least 2 full cycles of variation in order to treat a frequency as being credible. And that is a little bit arbitrary. It's not like it's governed by some mathematical rule, but I think it's a reasonable starting point. And so what that means for a 28-day Lightkurve is that I want the period to be shorter than 14 days. So I convert 14 days into a frequency, and I use that as my minimum frequency, because any frequency that's below that would not have a chance to repeat itself twice during the Tess observation. For the highest frequency, there's actually a mathematical rule that applies here, referred to as the Nyquist frequency. And the idea here is that if your data have even spacing between each subsequent measurement, which is very close to being true for Tess observations, there's a maximum frequency above which you can't fully recover a sinusoidal signal that might be present in the data. So it's kind of this hard upper limit. And the way that you calculate this is you take the interval between consecutive measurements. So for fast cadence data in Tess, that's 2 minutes. For full frame, for the first 2 cycles, that's half an hour. You multiply by 2, and then you convert it to a frequency. So I've given here with these 2 bullet points what that would be for Tess. So fast cadence, the maximum frequency would be 360 cycles per day. For FFI, it would be 24 cycles per day. And again, that's valid for cycles 1 and 2. It'll be different for cycle 3 since it uses different exposure times. With V-star, I don't know that I would want to necessarily search the entire frequency range because as powerful as V-star is, it's not as computationally efficient as some other implementations of period analysis. Like in Python, I can search that entire frequency range in a few seconds, but it could take longer than that in V-star, potentially significantly longer. So it's probably good when you're getting started just to do a more targeted search like what we did initially. And then maybe as you get more comfortable, you can start thinking about probing more of the frequencies that are accessible to you in the test data. Now that's a lot of talking, and we're down to 23 minutes. And I do want to get to the breakout sessions. So are there any questions or comments?
Colin, what typical alias might cause the little side lobes on the main peak in Tess?
So that's governed. So that's a little bit more of a technical answer. The long story short is that it's governed by the sampling of the data, something we call the window function. Kind of in the ideal case, if you just have one long uninterrupted Lightkurve, you will inevitably see those side lobes unless you have an infinitely long Lightkurve. So they're suppressed as you get a longer and longer data series, but you're always going to see them unless you have an infinitely long data set. The reason for that is it's more mathematical and involves Fourier transforms, which certainly for me, they're not my cup of tea. And I don't think it would be necessary to understand it just to be able to do this period analysis. I think the kind of the understanding I'd want you to have is just that it's related to the sampling of your data, whether it's basically how long your data series is and whether there are interruptions in it.
You know, what sort of interruptions on Earth? We get the daily and the monthly and the yearly. I guess you don't get anything like that in test data, fortunately.
Thank goodness, no. So each test Lightkurve is usually going to have an interruption for like a day or two in the middle of the sector when it's downlinking data. but that doesn't really impact the power spectra. When you're on the ground and you can only observe a couple hours a day, and then maybe it's many days before you get to observe again, the power spectrum just looks horrific because the sampling effects will cause, instead of just like one nice peak with those really low amplitude side lobes, all of a sudden you can get spurious peaks showing up at frequencies that are just dictated solely by your sampling. So those of you who have done power spectra with your own ground-based observations have probably seen this, where a light curve has one period in it, and yet a power spectrum will show a number of plausible looking peaks. And it's just because there are large gaps in your data.
There are
Luckily,
advanced
with Tess,
techniques
you
we
don't have to worry about it.
Yeah. If anyone ever sees something like that and is really interested in figuring out something's real, there are advanced techniques to try to account for that. And you can always email me at civicoff@ualberta.ca. I'm on, easy to find.
You get spoiled if you work on test data too long. I have to admit that you get just these pristine power spectra that look close to the theoretical ideal. And it's really tough to go back to ground-based power spectra then and seeing how messy they can look. So if there are no other questions or comments, I do think this would be a good point to pivot towards the breakout sessions. And looks like we're probably going to be lucky to get one, maybe two targets in per session. So the way we have this set up is that there will be two sessions, and you can jump between them. But I suggest, given the time constraints, you just choose one, depending on your interests. Eclipsing binaries and short period pulsators.
Excuse me,
So,
Colin, could
yes?
you let me share my screen, and I'll put up the slide about the two while you're
Sure.
talking.
All yours.
Thanks.
You might want to put the links in the chat too.
The links, everybody got an email with the links. So if you don't see it on the, don't want to write it down on the screen, just look in your email. We can put it in the, I guess we can put it in the chat as well.
Yeah, just in case.
So I think the way I'm going to do this, given the time constraints, I'm going to jump into the EB session first, because for the target I'd like you to look at, it really would benefit from that Finder chart software that I showed you earlier. So I'll stay in long enough to show you that, and then I'll hop over to SPPs. For SPPs, I'm going to suggest that you just, let me look at my targets I've got here. I would suggest probably might you go with AC Andromedy. It's going to have a complex power spectrum because it has multiple frequencies present in it, but it'll be good practice. And then after the workshop is over, you can, if you're so inclined, you can work on the other stars in the list as well. And I'll send a link to other stars that could benefit from Tess observations.
Colin, is the Zoom session going to mess with the webinar page at all?
The webinar is going to go away. The webinar is going to finish, and then we're going to split into the two breakout set meetings.
Okay.
So
And they are in parallel or after each other? I didn't get that.
they're in parallel. So you have to choose which you go to one or the other.
Okay.
And yeah, and I'll do this right now, and then Colin can go back. You'll need to give us a couple of minutes once we finish here, so that Sarah and I can both log out and then log in again to start the Zoom meetings. So the breakout session. So once we close the webinar, just give us a couple of minutes, and then just go to your Zoom link for the breakout session and just wait for us to open it up. It won't be more than a minute or two. Sorry, Colin.
This will be the this will be the last time that we're all on the same call. I just want to thank everybody for being here today, for their patience. And I will be sending all of the relevant materials later, probably in a couple days after I've had a chance to recover. But you've been wonderful, and I look forward to working with you in these groups.
Colin, thank you so very, very much. This has been tremendous. I myself have learned so much as a beginner with analysis, and I'm sure we've all learned many things and are looking forward to putting it into practice. I also want to thank all of you who have attended, who signed up for the workshop. It's great to see that everybody who signed up is here. And I'd also like to thank our sponsors for this workshop, QHY-CCD, OBSTEC, Optical Structures, and First Light. We're grateful to all of them for their support. And does anybody else have anything else? All righty, then we're going to end this webinar.
Thank you, Colin. It was wonderful. Thanks, Colin. If we don't.
Yeah, it was great. Thanks.
It was awesome.
Thank you very much.
Thank you, Colin.
Bye-bye. Hanging it up.
We'll see you all later, and thanks again.
On the other side.
Would
Bye-bye.
you please consider to make a choice course about this topic?
Great idea. Thank you.
Excellent idea.
Okay, thank
Thank
you.
you. Bye.
Thank you.